used to solve the difficult problem for the traditional numerical methods, such as the finite difference method. For example, PIN is expected to solve the ill-posed problem where the initial or boundary conditions are not fully available. Moreover, PINs is expected to become a novel numerical solver for the partial differential equations, since PINs can be trained only with the physics knowledge, like governing equations, without any data. In this research, we focus on these third properties of the PINs. So here I compared the properties of the PINs with traditional numerical methods. Since time is limited, I do not go to the details, but here I would like to emphasize that the formulation of the solution is completely different. As we know, in the traditional numerical method, the solution is always given by a discrete implicit form. In contrast, in the PIN, the solution is written as a continuous and explicit form of the, for example, the time and the coordinate system. As a result, we can expect the numerical errors caused by the discretization can be reduced in the case of the PINs. This is the one of the big advantage of using PIN for solving partial differential equations. Here is an example for such advantage. This is the result we obtained when we applied PIN to the 1D Vargas equations. The left-hand side, in here we compare the PIN results with the finite difference FDM results and also the analytical solutions. If the solution is very smooth, as shown in the left-hand side, the difference between the PIN and FDM is not so significant, but it becomes very remarkable when the solution has a steep region, like the one shown in the right-hand side. As you can see, when we use the finite difference method for this kind of the steep gradient, we usually observe the oscillatory behavior at these steep regions. But PIN solution reproduce very smooth solution and matches the analytical solution very well. On the other hand, the very big problem of the PIN is the training time. Here is another example. We applied the PIN to solve the two-dimensional flow over the cylinder. As shown here, we can successfully simulate the unsteady behavior, Kalman vortex, using PINs. But time duration is only 4 seconds in this case. And in our case, it took about 1 week, even though we use 8 GPUs in parallel. That's the big issue, the most important issue of the current PIN situations. So in order to address this problem, of course we have several directions, such as the tuning of the hyperparameters, number of neurons, number of the depth of the neural networks, or selection of the optimization algorithm. But here in this study, we focus on 2 different directions. One is the enhancing the generalization capacity of the PINs. In this approach, we try to use the same network for different flow conditions. As you know, generally speaking, PIN should be retrained when for example, the boundary condition is changed. But in here, we try to use the same PIN to solve the fluid flow for different boundary conditions. Another direction is the designing is more rather direct to the acceleration of the training of the PIN. In this approach, we are trying to design or optimize the architecture of the internal neural network of the pin. Yeah, the detail will be given in the later section of the presentation. Okay, yeah, to be more specific, let's start with the architecture of the pin we use for two-dimensional flow simulations. As shown here, since we are considering two-dimension, the input is the coordinate of x and y and the time t. And the output is the velocity u and v and pressure p. And of course, we have a neural network that connects input and output. And also, we can use automatic differentiation mechanism to evaluate the derivative of the output with respect to the input. And by using those results, we can evaluate the residual of the governing equation, PDE, and use those results in the loss function to train the neural network here. And again, yeah, of course, we can use several loss functions as shown here. But in this research, we focus on the data-free approach. So I don't use the data loss here. I just use physics loss here. But the problem here is that the boundary condition is only considered in the loss functions. So as I mentioned earlier, this pin has to be retrained when we change the boundary condition here. So in order to solve this problem, what we have to do is to use the boundary condition as the input for the neural network. In order to do this, in this research, we introduce what is called deep operator network, or deep ONet. Deep ONet is a new type of neural network that can run operators, meaning the functional mapping from the function to another functions. More specifically, in this research, we consider the boundary, the velocity distribution at the boundary as the input function, and the corresponding fluid flow as the output function. And in the deep ONet, internally, there are two different neural networks. One is called trunk network, and the other is called branch network. And each takes different input. Trunk network takes the input, the same input as the original pin, the coordinates, x and y, and sometimes t, if you need. And the new network, branch network, takes the input of the velocity distribution at the inlet, for example. Like this, from the original pin, we add a branch network like this. As a result, we can use the boundary condition as the input for the neural network. By using this network, of course, this network, in the training of this network, of course, we can use the concept of the pin, the same concept of the pin. We can use the loss function, the loss function for the partial differential equations. And so this network can be trained in a data-free manner as well. And we do it in this research. Okay. Let's have a look at the very small benchmark test program here. We consider a two-dimensional channel flow with an arbitrary inlet velocity distributions. Of course, in the classical CFD, we have to recalculate when we change the profile at the inlet. But now we are trying to see our network can predict the fluid flow for different inlet boundary distributions. In order to train this model, we have to give the sample profiles for the in the training. Here is an example of the velocity distribution we used in the training. The example are shown in the gray lines. As shown like this, we use, of course, of course, the network can predict more accurate results when we use more and more samples in the training. And in our training, we use at maximum 800 different distributions. Okay, this is an example of the validation result we conducted in this research. Here we give the very simple parabolic profile at the inlet and check the corresponding fluid flow is consistent with the analytical solutions. And here is the comparison of the velocity distribution and the pressure distributions. Generally speaking, there are some errors observed, but I think overall trends can be well reproduced by this network. But what we want to do is not, reproduce this single flow field. We want to reproduce another fluid flow field when we give different boundary conditions. Here is a validation for such different boundary condition. We change the, here we use the cubic profile at the inlet. Again, we can see the DeepOnet can reproduce, in this comparison, we compare the DeepOnet prediction with the open form prediction, open form results. And we can see that they have a good agreement between each other. So, these results show that our DeepOnet can be used for different type of the boundary conditions. This slide shows about the parallel training of our model, but since time is limited, I would like to skip this program. And here is lastly, I would like to show some demonstration for the advantage or for the merit we have when we use this DeepOnet. Again, this is the simulation result of the jet flow with different position of the jet. Again, if we change the position of the jet, we have to calculate the simulation again and again. But if we use this DeepOnet, of course, we have to train that network, but only once is enough. If we train the network once, we can use the same network for simulating different position of the jet flow, as shown on the right-hand side. Here is the first part of my presentation. For the second part presentation, I would like to summarize the neural network that are used for in the traditional pin architecture. We usually use, and also in my research, I always use the MLP in the base neural network. But I think MLP is one of the standard architecture, and it's mostly used in pin researches. But of course, we know this. It has some drawbacks. One most significant drawback is that it has frequency biases. So it's difficult to use in the high frequency phenomena. And also the one more important drawback is that it's difficult to interpret the physics of the MLP. And in order to solve this problem, some people are using the sinusoidal function in the activation function. As a result, that network can simulate the high frequency phenomena well. But still, the physics, the interpretation of the physics is still difficult. And aside from these traditional networks, new type of neural network is proposed recently, last year, I think, which is called Kolmogorov-Arnold network, or CAN. CAN is quite different from the traditional neural network in the sense that it can learn activation function itself. So as a result, CAN represents very complex phenomena compared to the traditional neural network. But in our preliminary test, even CAN is not successful for the high frequency phenomena, for solving the high frequency phenomena. So in our research, we do not use a single neural network. Rather, we try to combine two or more neural network inside and give each neural network a specific role for specific roles. For example, when we solve the when we solve the mass spring problems, we know that solution can be written as written by the some components for amplitude part and some components for the phase. So in our approach, we consider internal neural network that is designed for amplitude and that is designed for phase separately. Yeah, to be more specific, let's consider this example. As I said, we are solving the one-dimensional mass spring damper system in this research. And of course, we know the governing equation can be written like this, and the analytical solution exists and can be written like this. And this analytical solution has a component of the, amplitude part and oscillation part. So in order to solve this problem using PIN, we compare several architectures as shown here. First, we introduce a standard neural network like MLP, CAN, Siren. And also, we introduce combined neural network like this. As I mentioned, in this network, we separate the amplitude part and oscillation part like this. And each part are represented by different architecture network like this. On the right-hand side, the result is compared. This is the result for the one-dimensional mass spring damper system. But in the training, we only use the collocation points between the time 0 and time 0.5. So during this interval, the solution from the different architecture, most of the solutions are consistent with the analytical solution within this interval. But in addition to that, we check the extrapolation performance of each network. So we check the prediction result for from the time 0.5 to time 1 But here, as we can see, the prediction is not well, even for the, how can I say, no neural network can predict the solution within these regions. Yeah. And again, in this simple problem, the difference between the traditional neural network and this combined neural network is not very large, so we can see the difference. But when we go to more high frequency region like this, the difference becomes more remarkable. Again, here is the comparison of the solution from different network architecture. Roughly speaking, the traditional network failed to predict both amplitude and phase like this. But if we combine CAN and silent, we can predict both amplitude and oscillation phase very correctly, as shown in the pink plots. But still, the extrapolation performance is not very good, unfortunately. Yeah. Since time is limited, I would like to skip this page. And finally, I would like to show the comparison of the network for the two-dimensional simulations. But since we just started this research, so at this moment we have not yet conducted, hyperparameter optimization or something like that. So still, we do not have, significant improvement at this moment. But I believe the combination of CAN and silent can, help accelerating the training process of PIN in the future. I'm sorry, time is come, so I'd like to finish my presentation. Thank you very much.
Thank you, Dr. Junia. Questions? All right, so,
Hello. Yeah. So what kind of parallelization you have tried, like data parallelism or the model parallelism for the multi-GPU?
We just use data parallelism in this training, but we plan to model parallelism in the future, if possible.
Okay.
So if the flow has SOCs, so you think the CAN plus silent can do the predictions for that kind of flows?
For the fluid flow, yeah.
Yeah, with SOCs, normal and oblique SOCs.
So aerodynamic shocks, like where you have a...
Shocks,
yeah.
No. In this case, how can I say, we have not yet tested shock case.
Okay. Okay, yeah, thank you.
I think what he meant to say is if you have some sort of discontinuity.
Discontinuity.
Right, so,
yeah.
So like in finite volume or finite difference, you can increase the order of the spatial scheme to capture that. So if you have something like discontinuity, would CAN and Siren or one of these combinations would be able to capture that? I think that was his question.
I guess some more different architecture might be necessary to capture shocks, I guess.
Since you mentioned that high frequency is better captured here.
Yeah, high frequency can be captured by silent, I think. But shock is somehow different from the...
Any other questions? Okay. So let's thank the speaker again. Okay, so our next speaker is Dr. Richita Das. And she has graduated from Texas A&M and currently is in IISc Bangalore. And she primarily works in turbulent flows, CFD and data-driven modeling. And today she is going to talk about machine learning enhanced stochastic modeling of intermittent dynamics, and machine learning enabled inflow generation for turbulent flows. So, Dr. Das.
Hello? Yeah. Thank you for the introduction, and thank you to Professor Rajesh for inviting me to this workshop. I'm having a very good time here, and yeah, very glad to be here. Okay, so I'll start with a little bit of introduction on turbulence, which most of you don't need. But we know that turbulence is clearly present everywhere, all around us. It's not an exception, but rather the common reality. And if we look at something as simple as mixing of milk in the coffee in the morning to something as large scale as astrophysical jets or cloud turbulence, there's turbulence at all scales. So it's an important problem to study, understand, and model turbulence. But there are certain difficulties in turbulence, right? So it is highly nonlinear in nature, which means that we can't take two simple turbulent flows and put them together and make a complex turbulent flow. It is extremely chaotic in nature, which means that if we start with two different initial conditions which are very close and only a little bit different, they'll diverge and end up with two completely different looking flow fields. So just like shown by this Lorentz system example over here, it's extremely chaotic. It is multi-scale in nature, so you have very small scales and very, very large scales. So your simulation capabilities have to be such that you can capture the smaller scale, but also have a grid size large enough that it can capture the larger scale, which makes computations very expensive. And it's extremely intermittent in nature, so there are these extreme events that pop up, and capturing them, predicting them accurately makes a lot of difficulty, which is what we face in our weather predictions, etc., etc. So because of all these difficulties, numerical simulations in turbulence is very difficult, extremely expensive. So all bad news, but one good news is that the statistics in turbulence is very robust. So that is what makes turbulence modeling a possibility, because we are able to model some of the things which are kind of unique and universal across different turbulent flows. So that is what makes our life a little bit easier. There are different numerical simulation techniques which we all, several speakers have spoken about. There's of course RANS, LES, and DNS. In RANS you're mostly modeling the just the larger scales. You're not capturing the smaller scales, but it is reasonably cheaper. And then in LES you're resolving much of the scales, but you're not resolving the very small scales, which you model the effect of on the larger scales. And finally in DNS you're not doing any modeling, you're just resolving everything. So here we have to think about the particular application where we are applying it, right? So if we are applying it to a flow where we need a lot of fidelity, then we have to go with a higher fidelity simulation. Whereas if we apply it in a situation or in our application, we don't need that kind of fidelity, and we rather have a quicker simulation, lesser cost. So we have to think of that cost fidelity trade-off in turbulence. So I'll just briefly give an overview of what we do in our lab before I get into the research problem. I lead the Turbulence Physics and Computational Research Lab at ISC. And we are looking at, in terms of computations, given that this is an HPC and data-driven kind of conference, so I'm going to focus on what we do there. So in terms of turbulent computations, we do mainly DNS and LES. In DNS, we do pseudospectral DNS, where we are just doing periodic box turbulence. So this is when we are interested in studying the fundamental aspects of turbulence, where we just want to know what is going on in the very insides of turbulence, free from any sort of mean flow effects or any anisotropic effects, just turbulence physics. If we want to study, we would use this kind of a solver, which we have. We also do DNS of more anisotropic flows, where we want to study what happens to turbulence in the presence of a wall, what happens to turbulence in the presence of a free shear, things like that. We have an interesting way of doing this anisotropic DNS. We use this method called influence matrix algorithm, which basically is a method where we divide in the anisotropic direction, we divide the flow domain into smaller domains, and we solve the flow solution locally within the domain, and then we only communicate through the interfaces. Even though we are implementing a spectral method, we can get away without global communications and purely through local, not purely local, but somewhat local global mixed communication, but the communication cost reduces a lot, which gives us super linear scaling up to quite a few number of cores. And that is the advantage of this method. We are currently simulating 2 types of flows. We are also looking at Rayleigh-Bénard convection on this. We also do large area simulations, for which we are using Santosh and Chandra's explicit filtering LES solver. And what we are studying with that is mostly interactions of turbulence with shock waves and turbulent boundary layer. So, for example, if you have an impinging oblique shock on a turbulent boundary layer, it becomes a very unsteady flow phenomenon. The separated shock starts oscillating at a low frequency, and the separation bubble also starts breathing. So we are studying that using LES simulations. And we are also looking at a Scramjet intake problem, where we are studying the case of multiple such shock boundary layer interactions and their mutual interaction and the unsteadiness that is resulting from that. So in all of these problems, as you can see, the turbulence fluctuations are very important. So we can't really do RANs in these kind of problems because it does matter what kind of LES fluctuations, what kind of turbulent fluctuations are present and how they're interacting with the shocks, etc. So, of course, we study all of this from a physics perspective. We look at, we use more traditional conventional methods, but we are also using some newer age data-driven methods. One such method is information theory. I'll just briefly speak about it. It is actually a concept that comes from electrical engineering, and it's used quite a bit in complex system research across neuroscience, economics, ecology, etc., etc. But it's a very useful tool in turbulence because it is also a complex system, and there's a lot of chaotic interactions, a lot of emergent dynamics, a lot of self-organization going on. So we are using some of these tools to study turbulence as well. Information theory comes from Shannon entropy, which is, again, it measures the uncertainty of a random variable. And you must have, many of you must have seen this measure KL divergence, which in machine learning is used quite a bit, particularly in generative machine learning. KL divergence measures that how different is one PDF from another. So we are using that to study intermittency. For instance, how different is my turbulent PDF from a Gaussian random field. That gives me a measure of how intermittent is my turbulent field. So this kind of a thing can be applied to other intermittent signals as well. And we have observed some interesting trends. I will not get into that. We are also using the measure of transfer entropy, which is basically a very interesting measure. It's a data-driven measure relying on joint probability distributions, and it tells us about causality across random processes. So if you have 2 random processes, X and Y, how does X cause Y? It can give a good measure of that in some sense. So it basically measures the reduction in uncertainty in the future of Y due to knowledge of the past of X. So that is how it tells us about causality. It's like a non-linear dependence between the random processes. Typically, people have looked at correlations. That is what we always use. But correlations only pick up the linear dependence between processes. If you're interested in capturing the non-linear dependence, you would want to use something like mutual information or transfer entropy. Right? So we are using that to study a lot of different problems. I'll not get into that. And other than this, of course, we use singular value decomposition-based methods. We are using time delay embedding and machine learning, which I'll talk about. So focus of this talk is on two aspects. One is develop a highly accurate statistical model of intermittent small-scale dynamics and turbulence, which we hope will be important for future subgrid scale modeling. And second, we want to generate synthetic turbulent boundary layer for inflow applications in CFD, particularly in wall-bounded flows. All right. So the first topic is a work done by a BTech student from BITS Pilani who did his thesis with me. And in a matter of 6 months, he's done this work. So yeah, it's an interesting piece of work. So we are going to model the Lagrangian dynamics of intermittent small scale in turbulence. So scales in turbulence, as we all know, there's a broad range of scales. If we look at velocity contours, we can see that there are smaller scales and then relatively larger scales. If we plot the spectrum, we can see the whole distribution of scales. And large scales tend to be dependent on the flow geometry, so different flows will have different large scales. So it's difficult to model that. But small scales tend to be more universal and isotropic in nature. It is intermittent, and it is because the structures become more and more chaotic, it becomes more and more intermittent. But even in that intermittency, there's a certain universality present, right? So there are a lot of things that can be understood about the small scales from a simple box geometry like isotropic turbulence, where we can go up to very high accuracy and we can do DNS of high Reynolds number and things like that. So we can do that, achieve that in small scales in a periodic box, for instance. So that is what our plan is. We want to model the small scale dynamics in isotropic turbulence and apply to hopefully future complex turbulent flows. For that, we study the quantity velocity gradient tensor, which captures the small scale behavior of turbulence. As you can see from the Fourier transform, it linearly depends on the wave number. So higher the wave number, higher is the velocity gradient. Higher wave number means small scales, right? So it directly reflects the small scales. And you can also see the contours of velocity gradient magnitude, and see in a turbulent flow you have, it clearly represents the small scales. So we want to study this and model this. Now, we have shown in our past work that velocity gradient tensor can be broadly divided into two pieces. One is the sort of bounded geometric shape, which is mathematically bounded and is universal across flows and across Reynolds numbers, things like that. And the other part is what we call velocity gradient magnitude, which is basically the Frobenius norm of the velocity gradient tensor, or what we also call pseudo dissipation rate. So basically our dissipation rate and vorticity, sum of that gives us the pseudo dissipation rate. So in this talk, I'll be focusing on modeling this quantity, because this is the intermittent quantity in turbulence and small scales, and we want to first see if we can develop a model for that. So if you follow the Lagrangian trajectory of a particle in a turbulent flow, you will get a velocity gradient magnitude that looks like this. It has these very extreme events and very intermittent in nature. So the motivation to study this is that this kind of a model will help us develop models for deformation of droplets and bubbles that we saw in the talk yesterday. It can help us with subgrid scale modeling if we ever want to achieve small scale dynamics accurately at the small scale, which is generally not been attempted in LES. If you want to achieve that also correctly, we just model the dissipative effects, we don't model the dynamics. But if you want to model the dynamics, this kind of a thing will be useful. So previously, people have tried, and there have been a lot of models, but they've been unable to capture the intermittency very accurately. So our approach is to use a more physics-based framework and then enhance it with machine learning. So one of the models that we picked up was by Dr. Girmaji and Dr. Pope from 1990. And this model uses this log normal framework called Ornstein-Uhlenbeck process. So this process basically gives us a nice stochastic model framework that leads to a normal distribution. Now, if you do this for a log of a variable, you will get a log normal distribution. And it's a very commonly used process in finance, etc. A lot of systems use this. So this stochastic differential equation typically has like a drift term, which captures the mean dynamics, and a diffusion term, which captures the fluctuations, okay? So in the diffusion term, the dW basically represents the increment of a Wiener process. So it tells us that how much fluctuation is there, right? So that part is the diffusion term. And this model depends on two simple parameters. One is a variance, another is a time scale ratio. And any stochastic differential equation has an accompanying Fokker-Planck equation with it, which basically tells us that how the PDF is going to evolve, because the stochastic model gives you the evolution of a system following a certain PDF. So how that PDF will evolve as a function of time is given by this Fokker-Planck equation, which is a differential equation of the PDF F. Okay, PDF here is probability density function. So now if we apply this to DNS datasets, what we observe is it's pretty good. I mean, in the peak probability region, it's a decent model. But if you look at the very low dissipation events or extremely high dissipation events, then there the tails kind of fail to capture the extreme events as well as the, the very low pseudo dissipation events. I also talked briefly about a measure of intermittency. So if we use KL divergence to study intermittency, we can see that this model will kind of deviate a bit from the log normal model. Okay, so so we need to improve this. What we said we'll do is we'll just modify this Ornstein-Lehlenbeck process, and instead of having these constant coefficients, we'll take them as a function of the local pseudo-dissipation rate. Because pseudo-dissipation rate, like many other turbulence quantities, is very intermittent in nature. Its local thing is very different from the global thing. So let's do this modeling based on the local pseudo-dissipation rate or velocity gradient magnitude, right? So to do that, we can use a simple neural network, just an MLP, and get the sigma and the tau as a function of our phi. But will this satisfy the correct PDF? Not necessarily, right? So we need to do something to get the achieve the correct PDF using this stochastic model. So to do that, we need to look at the Fokker-Planck equation. We need to make sure that this Fokker-Planck equation actually has a stationary solution. That is, the DDT of the F PDF goes to 0, right? So the right-hand side of the Fokker-Planck equation is what we want to make sure. This right-hand side of the Fokker-Planck equation is what we want to make sure goes to 0, so that it has a stationary PDF solution. Our stochastic model goes to a stationary probability distribution. That is first. The other thing we need to make sure is it goes to the right solution. It goes to the DNS PDF that we want, the ground truth. So these are the two things we need to make sure of. So we use a sort of a physics-informed neural network approach. We put in our input, but instead of just predicting the coefficients of the model, we are also predicting the PDF F. And then we simply, using backpropagation automatic differentiation, we can calculate the derivatives, we can get the loss function for our Fokker-Planck equation, which is what we call the Fokker-Planck loss, right? And then in addition to that, we also need to make sure that the PDF not only goes to a stationary solution, but also it goes to the correct stationary solution. So for that, we can do a mean square error loss. And we just take our PDF, subtract from the DNS. We add a log so that it helps capture the tails better. So we add a log to that. And this is the loss function we are optimizing for. Ultimately, we end up training this model so that we can get these model coefficients sigma and tau as a function of phi, and the PDF F phi. And ultimately, the stochastic differential equation should achieve this stationary solution. Right? So we train this over a period of time, and we observe the physics loss and data loss reduce. You can see the value of the physics loss is actually very small, and we need this. Otherwise, the stochastic differential equation doesn't converge to a stationary solution correctly. But our KL divergence also converges to the DNS value in training. And ultimately, we get these coefficients from the model once it is trained. We get these coefficients as a function of the local phi, and we put that back into our log normal stochastic model, which is now a modified log normal stochastic model because we have modified the coefficients. So it has become a modified log normal model. And now we simply propagate, we apply this to, let's say, 20,000 particles. Think of Lagrangian particles in a turbulent flow. And we try to start them from a Gaussian random field. So initially, it's not turbulent, all random. And then over time, so initially the PDF is basically a gamma PDF in a Gaussian random field. From that, it evolves towards a turbulent solution. That's the hope, right? So we follow the evolution of these particles, and we see that these are the moments. So all these 200,000 particles, if you collectively look at the evolution of their moments, the first order moment is simply the mean. Because we are looking at mean normalized quantities, you will see it goes to 1. And so on, second order moment, third order moment, fourth order moments, which become more and more intermittent, which is what we expect in a turbulent flow. So higher order moments will look very intermittent, but they converge. They converge to a stationary solution in time. If you look at the converged probability distribution, the one we started with is this blue one. This light blue one is the Gaussian one that we started with. But over time, our model gives us a PDF that looks like turbulence. So the converged PDF is very close to that of DNS. And if you compare with this red dashed line, which is the log normal model, we are able to achieve the tails and the very low dissipation events slightly better. Also, this part is a little bit better. So yeah, some improvements, right? And in terms of the intermittency itself, we can see the KL divergence is also captured better. In terms of time evolution, our the time variation looks a little more noisy than what we expect in DNS. We're looking into why that's happening. Autocorrelation is also showing an exponential decay, but there are a little bit differences from DNS. So we are now looking into that. The next thing we thought about is how to incorporate Reynolds number dependence in this, because if you vary Reynolds number of the flow, the intermittent nature of the small scales also changes. It becomes more and more intermittent. The PDF becomes more and more heavy-tailed. So how do we capture that? Again, we use a neural network, but this time the Reynolds number is also an input to the model. And ultimately, our coefficients come out functions of both local phi as well as the Reynolds number of the flow. And we train it on different isotropic turbulence data sets, and we finally test it on one which is in between, not an extrapolated regime, but an interpolated one. And what we observe is we capture the Reynolds number trend accurately. It is becoming heavier tailed more and more. And finally, it converges to probability distribution, which is very close to that of DNS for an unseen test case. The intermittency plot is also better. As you can see, previously with the log normal model, it was diverging a bit from the DNS. But you can see the ones we have now are the red dots. The red dots are better in terms of capturing the intermittency. So overall, with this part of the talk, what we have achieved is that we have developed a machine learning enhanced modified log normal model, which gives us a good sort of Lagrangian model for prediction of how the velocity gradient magnitude will evolve as a function of time in a turbulent flow. And it's a stochastic model. So the idea is to capture the correct probability distribution, not just the individual trajectory, but the probability distribution, just like we do in our generative machine learning. But we have used a physics-informed neural network approach to solve the inverse problem of Fokker-Planck equation and get the coefficients of the model from it, right? So that's how it has been used. And we have seen some good results. The second part of the talk, which I'll get into, how am I doing on time? Okay, since the session chair is not saying anything, I'll continue. Okay, so the second part of the talk, I'm going to speak about a generative machine learning model for synthetic turbulent boundary layer. This work was done by a project associate who's currently at IIT Hyderabad. Okay, so wall-bounded turbulent flows, one of the difficulties is creating the transition, right? Transition requires very high resolution, sometimes DNS-like resolution to capture the transition accurately. So even in an LES simulation, we would have to refine the mesh a lot to capture the transition at the correct point and things like that, right? So, and it also requires a long development length. So that wastes a lot of grid points, a lot of computational resources go into it. So we actually need to develop better turbulent inflows, turbulent boundary layer inflows near the wall where we require a lot of resolution and the triggering of transition is very important. So in these kind of problems, we need something from machine learning to help us generate better and better inflows for us, right? A lot of applications require these kind of inflows. So how do we do that? Basically, let's say we have a turbulent boundary layer developing like this. We are trying to avoid doing all of these simulations, right? So that we can just provide this plane as a function of time. So this sort of YZ plane as a function of time, if you can provide a spatiotemporally coherent turbulent boundary layer field, something that looks like turbulent boundary layer, like a synthetic turbulent boundary layer, which is spatiotemporally coherent, and you put that into your computational domain, then you only need to simulate this part or whatever comes after this. You don't need to do the whole thing, right? So that is the aim. That is what we want to achieve. There have been a lot of previous models which have tried to attempt this, and they are working well. I mean, I wouldn't say these are present in your open source solvers as well, like OpenFOAM, etc. For instance, digital filtering, recycling, rescaling kind of methods. There are many more. But there are some disadvantages to these methods. One is that the accuracy of spatial temporal statistics is limited up to second order only. So we do the digital filtering in a way that you only impose up to second order statistics. then there are sometimes these spurious correlations, right? If you're doing a method like recycling, rescaling, where you're taking a boundary layer downstream and then you're putting it back in from the beginning, it'll create a new temporal correlation scale which will appear in your boundary layer. So there are these kind of issues. Also, most of these methods require running an a priori construction, like a priori simulation or construction, and then you store that synthetically generated data, and then you feed that into your simulation. So you're always limited in storage as well. Or you store a small amount and then you recycle it in your simulation. Again, you will bring in a spurious correlation. So we wanted to use these for shock boundary layer kind of problems where we have a low frequency unsteadiness. So if you already have a low frequency unsteadiness in the flow, introducing other spurious correlations can be very bad, right? Can interfere with your results. So that's why we want to generate a synthetic turbulent boundary layer that will accurately capture the spatiotemporal statistics in real time without having to store large data. Okay, so we use the autoencoder framework, which you learned about yesterday quite a bit. So I'll not go into the details of it. The autoencoders basically learn the low dimensional representation of the data set. So if you put in your turbulent boundary layer, which is a 2D field in our case, because we just want the inflow plane, so a 2D plane, and you apply encoding, it will result in a latent vector, which is a compressed, small, lower dimensional vector that has all the required information necessary to reconstruct back the original turbulent field, right? So this encoding and decoding we do using convolutional neural network, because convolutional networks basically help in encoding the spatial structure of the flow, or in general it is used for image processing, so it captures the spatial structure of the image. So similarly here it will capture that. That is the idea. And then convolutional autoencoders will learn to encode the spatial features into a latent vector. That's the idea. So this part, the autoencoder part, if we train on a simple LES data, what we would observe is we get a very nice match of the generated with the, the ground truth. If you compare the statistics of log law, viscous sublayer, Reynolds stresses, energy spectrum, everything comes out nice. And so this means that we are able to effectively encode the turbulent boundary layer flow information into a latent space nicely. No problems with that. Now what do we do with that latent space, right? So we need to model that. We have encoded it, we have gotten the latent space. Now we need to use a time evolution model perhaps, or a generative model that will give us this latent space as a function of time. So then after that we can just decode it, right? Once you have these latent vectors as a function of time, you decode, you get back your turbulent boundary layer, yeah? So this is what we want. Ultimately we want a spatio-temporally coherent inflow turbulence, right? So to do that, we are going to use a diffusion model, because diffusion models are very good at generating these kind of fields. It's a generative machine learning model. What we do is we arrange the latent vectors side by side, forming in a sequence, forming a latent image, right? So this sequence of latent vectors, which has the spatial information on the rows and the temporal information on the columns, we try to learn how to generate this latent image using diffusion models. So the diffusion model, how it works is it adds noise. You keep adding noise to any image, it will eventually become Gaussian, right? So once it has learned how to add noise, it also learns how to remove noise. So denoising, the reverse process. So it learns how to remove the noise, and ultimately, once it learns how to remove the noise, now you have a system, or you have a model where if you just put in pure noise, you will get your spatio-temporally coherent latent sequence out of it, right? So you'll get your latent image out of it. So that is what we use. But diffusion models are expensive. How long of a sequence can we really train with it, right? Again, we'll be limited by that recycling, rescaling kind of process. So we don't want to do that. What we do is we add another recurrent neural network to this, which is a gated recurrent unit, simplest form of recurrent neural network, 2-layer GRU, and we apply that to this so that our diffusion model is used for the initial seed generation, because it's a generative model. After that, we just use GRU to propagate it forward without any limitation on that, right? So that is the idea, and this helps us reduce the cost significantly, because diffusion models are limited in how long can you run that. Without having to recycle the same data, we can achieve better with this. So now this is the overall architecture, just kind of summarizing all the parts together. we have a real data which goes into the encoder. Once encoded, we have the latent vectors. Latent vectors arranged sequentially gives us the latent image to capture the spatiotemporal resolution. Then we apply a latent diffusion to learn how to generate this latent image, and then a GRU to propagate it forward so that we get a longer sequence. Finally, once we have a long enough sequence, then we can always decode and get the turbulent boundary layer out of it. Okay, so this is the overall model architecture, and these are some results after training. So this is from an LES simulation, this one. And as you can see, the fields generated with the GRU-aided latent diffusion model match reasonably well. If you look at the autocorrelation decay as a function of time of the streamwise velocity field, we are also capturing that. So the spatiotemporal field is being captured very accurately with the GRU-aided latent diffusion model. Statistics also come out fine. I mean, we have a good match with the mean velocity profile, Reynolds stresses, and energy spectrum. Which means that we are not only capturing the second order, up to second order, but also probably higher order statistics. We still have to look at moments and things like that, which we haven't looked at yet. Yeah, so overall, to conclude, we have developed a machine learning framework that generates the turbulent boundary layer inflow with accurate spatiotemporal dynamics. It's potentially free from spurious correlations as far as we have observed. It is capable of real-time operation without any pre-stored data, and hopefully in future we can generalize to other flows, other types of inflows. With that, thank you very much for your time, and happy to take any questions.
Thanks, Rishita. Questions?
Thank you very much for the wonderful talk. I have one question regarding your second part. The purpose is to generate the inflow data for some turbulence simulation, right?
Yes.
So in that case, if you continue the simulations, the conservativity of energy or the momentum, or especially the mass conservativity become very important. In case you generate the turbulence in such a way, how much such a conservativity is maintained?
You're talking about mass conservation?
Conservativity, yes.
That's an interesting question. We didn't impose it specifically, but right now we have applied it to incompressible flows only. We are going to adapt this for compressible flows. So our mass conservation is coming from the divergence-free constraint, which we are imposing. So that is being imposed. So the dilatation the velocity field is dilatation-free. So locally, at least, continuity equation should hold. We expect mass conservation to also uphold, but we haven't tried to integrate the mass conservation to verify that. Thanks. Yeah.
Hello. So my question is like, I have two questions. The first question is it a simple autoencoder or is it a variational autoencoder?
It's a simple autoencoder, convolutional autoencoder.
Sure,
Yeah.
sure. And what does the latent space learn? I mean.
So the latent space basically learns like a way of representing, like Professor Raja spoke about yesterday. It learns a way of encoding the turbulent flow information, which can be, I don't know, 1,000 by 1,000 grid points in a 2D plane. We don't need all of that. Some of it is important, right? So we can just encode that information which is required to a latent vector, and then that decodes it back to the fully reconstructed field, right? So that latent space basically learns what is the lowest order or lower order representation of that full field. We may not need all of it to generate it back.
Yeah.
That's what I'm saying.
One more question. Generally, when we use the variational autoencoder or the autoencoder, like we generally say that the autoencoder creates a discrete field basically, and the relation between its latent space are very confused in normal autoencoder rather than using the variational. Like variational autoencoder literally separates out the different dimension in a much finer way.
Okay.
So why don't you use the variational autoencoder?
Why haven't we used? So variational autoencoder brings in the generative aspect. So you have to add, like, it basically is more like a generative model. So if you're trying to construct scale, for example, in super resolution kind of problem, you can use, we do use variational autoencoders for super resolution kind of problem. But here our purpose is not that. We want an exact latent space We don't want any added stochasticity into it, just the latent space. And then we want to see how does it evolve, can we generate it, can we generate new next time step, and so on. So we are not really interested in bringing in the generative aspect in the construction of the latent vector. If we were, then variational autoencoder would be useful.
One more.
Yes.
So, like in variational autoencoder, the different latent space shows the different dimensions of the flow field. I mean,
Okay.
in different, I mean, you can say different dimensions, basically.
Okay.
So, can you add a different, one more temporal latent space that could basically predict some kind, you have to give some kind of condition for that latent space, like for the other latent space, we give some kind of KL divergence and other conditions. Similarly, we can give a condition for the temporal learning to a particular latent space.
You can, but the problem is it becomes 3D then. So we are using convolutional layers, which are already very expensive to train. So if you have X, Y, or whatever, Y, Z plane, let's say wall normal and span-wise planes, on top of that you have time as the third dimension, which is what we tried initially with a GAN kind of a network. It becomes a 3D convolutional layers, which is very costly. It's not scalable at a smaller setup. Probably some big GPUs you do that, but if you want to work in a sustainable way, better to work with 2D CNNs. So in that case, if you add the temporal aspect here, it adds another dimension to the CNNs, which gets very costly.
Okay, thank you. Thanks a lot.
Yeah, thanks for the very interesting talk. In your second problem, which you discussed on generating the inflow turbulence for the, getting rid of the precursor simulation for this. So have you considered the Reynolds number effects?
Not yet, no. But that is in plan, yeah, next. But yeah, that will change the boundary layer for sure. Right now, whatever we are training on is what we are testing on as well. But yeah, the next step would be to make it Reynolds number agnostic. Yeah.
So the question here is also like, typically in digital filtering approach or recycling and reconstructing sort of like approach, like you already have some sort of like mean velocity profile and Reynolds statistics, mean Reynolds stresses in place, right? Which straight away asks you to now only worry about adding some fluctuations on top of this mean, right?
Yes.
So, but in your model currently, like it doesn't look like you have this mean in the first place, right? Because that in itself would take good amount of the turbulence statistics.
So you mean we are not imposing it like it is done in digital filtering? Yeah, we are not doing that. We are not imposing the mean and the fluctuation separately. We tried training that way, but that was worse. We tried to train just the fluctuation separately, but it was worse. It gave us a better model with both together. But that is also an architecture you can look at, but I don't see the advantage because, see, we in our heads, we divide turbulence into mean and fluctuation, but actually the flow is, one thing. So it's all together. So ideally, we hope that these kind of models can actually capture more higher order statistics. We haven't tested that, but we hope that it can capture even, more correlations and things like that, which digital filtering doesn't impose. Yeah.
Yeah, thank you.
Yeah, so continuing on Prashant's question, so right now you're trying to understand the latent space and then you apply diffusion model there, right? If you use variational autoencoder, maybe you can combine both the steps, so you don't have to interpret what latent space is, and then you apply diffusion on that, right? So
yeah, we thought about that. I know what you're saying, but I think if you try to bring both the things together, it will become inadvertently a 3D network, because time is the third direction. We want spatiotemporal statistics to match, and it is also 2D. So now if we mix the two, the problem that will happen is it will become 3D, which is what we were doing with GANs first. And while it was good results, it was not scalable. So we moved to this. Because that's why we separated the spatial and the temporal parts so that it can be scalable.
Yeah. And what is the cost compared to, let's say, digital filter or?
We didn't do an exact precise estimate, but cost-wise, I wouldn't think it will be very different, because here also we'll go through convolutional layers, which are like filtering operations in some sense. And then digital filtering also, you're taking a random field and you are applying a filter.
So can you generate it, let's say you want to run for 1 million iterations, so can you generate all those?
So the
beginning
idea
itself?
here is that we can generate in sequences
Okay.
with the GRUs. We can keep generating one time step at a time. Digital filtering, what they do is typically they store it, the whole thing they run and then they store it and then it is recycled and used. So that is one advantage, that you can generate in real time and predict the next turbulent field plane.
Yeah. Okay. Thank you.
Right, so I'll just ask something. So these data that you have got, so one is LES, the other one are some from your modeling, right? So when you do an average to get these U plus, are you just doing it on a 2D cut?
Also in time. So span-wise averaged plus time averaged, because we are generating.
So just the span-wise, but you are not doing a stream-wise average because you don't have that.
No. But we are also applying it to, we have tried both with turbulent boundary layer and channel. Channel you can do stream-wise, but turbulent boundary layer you can only do span-wise.
It's especially evolving one. Okay. The other one is in the first part you have shown that you have match with RE lambda, right? So for when you introduced Reynolds number in your network, so you said that it matched well with the Reynolds number, right?
Yes.
For different RE lambdas. So I believe this is the Johns Hopkins data set or something, is it? Or
yes,
you generated
one of them. The testing one was Johns Hopkins, yeah.
Okay, so so you said that for RE lambda it was matching well and you are getting this. So up to what RE lambda you have done this?
So we have only trained it on 200 to 600
that is
RE lambda. And then we have only tested it within it. We didn't do it in an extrapolated regime. We didn't do like, I don't know, 1000 RE lambda. We haven't done that yet.
So anywhere, so some lower bound and upper bound and in somewhere in between you have tested it. It works out really well.
Correct. So the aim is to be able to, we need to train on more data sets to be able to achieve extrapolative abilities, I think. We haven't tried it, but my guess is it won't do well beyond 600, up to which we have tested. So, trained. So yeah, the hope is if we train on more and
I mean you need a bigger, I should say, range. To
yes,
do that.
yeah, that's true. Yeah.
We
are running simulations now, so once we have.
Okay, so we can have a chat later as well. So let's thank Rashita again. So our next speaker is Dr. Niranjan. Who is there? So Niranjan graduated from Purdue, and I believe we first met in CTR, I think 8-9 years ago. So we met in CTR 8-9 years ago, I believe, in Stanford. And since then I know Niranjan. So Niranjan does large eddy simulations of turbine wakes. He has been doing that, and shock turbulence interaction. And he's going to talk about uncertainty quantification, sensitivity analysis, and physics-informed neural network-based coefficient estimation in wind turbine wake modeling. So, Niranjan.
This is the thing that goes in? No. Okay, I need to plug something in here, right? For this to work.
is a USB connector that goes in, so that this I can change slides using this. No, it's not working. There is a USB port or something. No, the pointer is working, but the slide, to change the slides, there is some pin that has to be put in here, which I don't find here. This one?
Can try. No, next one. I think where are the electronics people?
Okay, yeah, that was it. Okay, thanks a lot for inviting me, Rajesh and Pradeep. And Anikesh, the last time I was at IIT Kanpur, he was the session chair for that session. It's a pleasure to be here. I'm learning a lot in the last day or so. So I'm at IIT Hyderabad, and I've been working on wind turbine wake modeling, doing LES and simplified model development. So we'll talk a little bit about that today. So I'll start by acknowledging my students. They spend hours and hours in the lab, which is why we are able to work here or speak here. So I'm particularly going to talk about the work done by Utkarsh and Aryam, who have contributed to this work. So just to begin with, this is a map of India with contours overlaid about or contours of the wind power potential available at a certain height. In this case, it is 100 meters, and the estimate is that there's 300 gigawatts of power that can be extracted from the wind that is blowing there. If you look at the installed capacity as of 2025, it is really good, 50 gigawatts. Capacity factor and the actual penetration is not as good as the installed capacity. So what this points to is, among many other things, we still need to study the fundamental fluid dynamics of wind farms. Of course, a lot of other things have to go in for these two numbers to go up, but fluid dynamics is a part of that. So this is the fundamental fluid mechanical challenge with wind turbines. So you have a turbine installed on the ground, you have a turbulent inflow, and behind the turbine you will have a turbine wake where there is a velocity deficit or a hole in the momentum because the turbine has extracted energy, and you have increased shear, increased turbulence, and such effects. As a result, of this velocity deficit, or as a result of this wake, what you have is, in a wind farm, you have many turbines in relatively close proximity to each other. And because of that, very often one wind turbine sits in the wake of another turbine. So this is a very famous picture of an offshore wind farm called the Hornsrev. The Hornsrev wind farm. And what you see here is there is a line of turbines, and this is a particularly bad situation under which this photograph was taken, where the wind is perfectly aligned with the line of the turbine columns. So you have this front line of turbines which is generating the rated power, but all the turbines that line the wakes are affected because of the wake of an upstream turbine. And these losses of downstream turbines because of upstream turbines are called wake losses, and they can be really, really large, say even up to 60% under situations like you see in this photo. So if you just think about a wind farm and think about what all are the features that affect wake losses, the first quantity that affects it also is of course the spacing between individual turbines, so Sx. In general, in 2 dimensions, you have Sx and Sy. You have horizontal spacing, which is also called horizontal layout. Then you have the incoming turbulence, the atmospheric inflow turbulence that is going to affect wake losses. Then you have secondary effects such as stratification, you have Earth's rotation, you have processes happening in the ground, reflection and emission, incoming solar radiation, all of these are going to play a non-significant role in determining wind losses. And each of these phenomena have their own time scale and length scale. So you have the size of a typical turbine today is of the order of magnitude of 100 meters. So that is one scale. You have the boundary layer, which is a few kilometers. That is another scale. And you have many time scales as well in this problem. So this makes it a very interesting and a challenging problem to study. So there are several open questions related to how do you extract energy at the minimum minimum cost. There are also other equally important problems that you need to answer. For example, what is the effect of a wind farm on local micrometeorology or the local microclimate? Similarly, maybe say for more acceptability of wind energy, you need to minimize the noise propagation from a wind farm. So the cost associated with a wind farm is not only in terms of the actual cost that it takes to produce power, but also these other costs which are equally important to address if we want to push those numbers. So what I have been working on in the past few years is trying to incorporate conditions that are more relevant to India into these simulations and the models. So one example is here. You have surface heterogeneities. So you have a land surface and a water body close by. If you have a wind turbine that is in such a situation where you have these surface heterogeneities, what is the effect of these surface heterogeneities on the wind farm performance is what we are trying to understand. Another thing that we are focusing on is the effect of uneven terrain. A lot of our wind resource is in hilly terrain, for example, in the Western Ghats. So understanding effects of terrain where the elevation changes are of the order of magnitude of the wind turbine tower. That's another area of focus as of now. So our current research focuses on these two things: surface elevation changes and surface roughness heterogeneities. What I'm going to talk about is not wind farms, but of a single turbine today, on a single turbine. And I'm going to talk about high fidelity LES, uncertainty quantification and sensitivity analysis, in keeping with the theme of this workshop. And I'll talk about a little bit about the baby steps that we've taken in using pins for weight predictions. So the LES code that I use is a simple LES code to solve the incompressible Navier-Stokes equations in a Cartesian box. And we use high order numerics, Fourier spectral along two directions, sixth order compact scheme in the vertical direction. And we use a fourth order Runge-Kutta time stepping. So this has been under development since 2017 with colleagues from CTR. And it's an open source code. If you want, it's available to download. We keep contributing to it. And it is modular. It uses modern Fortran. It is MPI parallel. It uses the 2D comp and FFT library, which Pradeep talked about yesterday. There are a bunch of subgrid scale models that have been implemented, Sigma, AMD, modulated grain model, and so on. I want to highlight two simplifying assumptions that we need to make to enable these kind of simulations. One is that we don't resolve the flow features close to a turbine. What we are interested in is what happens at the farm scale. So after, say, a 1 diameter downstream of the turbine is what we are interested in. So we don't really care about what happens very close to the blade or the tower of the turbine. So we use what are called actuator disk or actuator line models. Rather than resolving all the details of the flow, we just inject body forces in appropriate positions with appropriate magnitude in the solver. The other simplifying assumption is close to the ground. It is impossible to do wall resolved LES here because these are geophysical Reynolds numbers. So we use wall modeled LES, and we have simple, there is a range of wall models, some appropriate under some conditions and some not. So we use wall modeled LES rather than wall resolved LES. And that is how this entire problem becomes tractable. For complex terrain, we use an immerse boundary method. So this is, an extension of the conventional immerse boundary method where we've adapted this immerse boundary method to be applicable to global schemes. If you have a low order code, you only need to populate those ghost cells adjacent to the immerse boundary in the solid, which are required for your stencil. The size is dictated by your stencil, the differentiation stencil size. In our case, because we are using Fourier spectral methods and compact schemes, we need values to be populated everywhere. So that's one small modification to previous immerse boundary methods that we've seen in the literature. So this gives us second order accuracy close to the boundary. Far from the boundary, we continue to retain higher order accuracy. In terms of scaling, the code is only CPU parallel as of now. It scales reasonably well. So this is one test on 67 million grid points. This is one test on 1 billion grid points. These were done back in 2018, so these are slightly dated numbers now. The important metric is that a granularity of about 60,000 seems to work well for us. And so the credit for all this is entirely the 2D comp and FFT library. They're doing these 2D the all-to-all transposes in a very efficient manner. And our credit is only that we don't break their scaling. Whatever additions we've done, we've tried to not mess with the scaling that they achieve using 2D comp and FFT. So I'll show few results about validation. So this is a single turbine. You have a turbulent inflow coming in, and you see this wake region, the region with reduced wind speed and a rich multi-scale structure here. If you take one particular cross-section here, say 5D downstream of the turbine, and if you look at the statistics, this is the mean velocity, this is the streamwise turbulence intensity. It agrees well with the experiments. This is flow over a hill, and this is an animation that should work. Okay, so this is a nice smooth Gaussian hill, and you have flow coming in. You have the wake of the hill, and you have a recirculation region. All of this is well captured. Again, these are the mean streamwise velocity profiles. These are the turbulence intensity profiles agreeing well with experiments, wind tunnel experiments. This is a stratified simulation. So this is, you have a convectively or a convective boundary layer. So you have shear from the top, and you have heating from the bottom. So there are two forcings to this problem, and what you see here are contours of vertical velocity. So regions of blue are downdrafts, and regions of red or yellow are updrafts. And you can see that the updrafts have a particular structure reminiscent of the hexagonal cells that you see in the Rayleigh-Bénard convection. But there is horizontal shear as well for forcing here. Again, these are our results on different grid sizes agree well with previous results. So these are mean velocities. This is the buoyancy flux, and so on. This is flow over a heterogeneous surface. You have a transition between a rough surface to a smooth surface here, and between a smooth surface to a rough surface here, reminiscent of the land-sea transition that I showed you, land-water transition that I showed you a few slides back. What happens is, if you have an incoming boundary layer that is in equilibrium, it undergoes a surface roughness transition. There is an internal boundary layer that grows downstream of this surface roughness change. And if you put probes at different locations, you can recover, or what we see is we recover the correct spectrum. The large scales in a boundary layer follow this k⁻⁻1 spectrum, and the smaller scales follow the Kolmogorov spectrum. So we evidence of both of those. And again, we have good agreement with wind tunnel experiments. This is one example of a smooth to rough transition experiment. These are, I guess, the mean velocity profiles, both upstream and downstream at different places. So lastly, we can take this all the way to a wind farm. This is a 10x3 wind farm. You have all these small, these white lines here represent turbine rotors. You're looking at this farm from the top, and you have flow coming in from the left. And what you see is each turbine lies in the wake of its upstream turbine. The wakes, they meander in the, or they flap in the horizontal plane with a fairly low frequency, which is dictated by the scale of the incoming turbulence. So all of these qualitative features are captured correctly. And again, we have good agreement of the mean velocity and turbulence intensity at different distances behind different rows in this window, captured predicted accurately by our LES. So that was a brief overview of our code. It is well established, well validated. We continue to add modules to it, and we are using this for our studies. So the next topic I want to talk about is uncertainty quantification and sensitivity analysis, with a focus on what happens in the wake of a single turbine. So if you look at a wind turbine, there are the vicinity of the wind turbine has, or the wake region can be classified into three parts. One is an induction zone, so a turbine also has some influence upstream of it. That's called the induction zone. Then you have the near wake region, and then you have the far wake region. So the near wake is maybe 3-4 diameters downstream, and beyond say 4 or 5D onwards, that is the far wake. And we are interested in modeling this velocity deficit here. What is crucial for wind farm wake analysis is this far wake region, because typically you don't have two turbines closer than say 5D. So the far wake, getting the model right in the far wake is what is important. So if I take the upstream velocity profile, the undisturbed velocity profile, and subtract the downstream velocity profile from it, you get this velocity deficit. So this velocity deficit is a bell-shaped curve. It is approximated well by a Gaussian. So it can be described by what happens on the center line, the deficit delta U at the center line, delta UC, and the width of this bell-shaped curve, sigma. So what you can do is you can write down this velocity profile, U as a function of x, and the radial component R as UC, that is on the center line, followed by a Gaussian. This is an approximation, and it's fairly closely adhered to. The width of the Gaussian is sigma, and there are many models for the wake width. One particular model which is developed from first principles is this model proposed in 2022. So this model for sigma has two parts. One is because of the ambient turbulence given by, or the ambient turbulence is quantified by a Schmidt number. And you have an S prime, or another component which is dependent on the mixing rate, or the spreading rate of the mixing layer that develops because of the turbine. So there are two components, and so the superposition of these two gives you the mixing width according to this particular model. For the centerline velocity deficit, there is a model given in 2015. And then you see a parameter T here, which is nothing but the travel time, which is the time that it takes for a fluid particle to travel a distance x from the turbine. So essentially, you have four equations. These can be iteratively solved. And you can come up with an estimate for sigma, the wake width, and the centerline velocity deficit, or the centerline velocity, either way. And what we see is, so this entire framework depends on 3 tunable parameters. There are more, but we've reduced that to 3 for the moment. So those are turbulent Schmidt number, mixing layer spreading rate, and one parameter called the Lagrangian to Eulerian timescale ratio, gamma. And in these studies, in this study that proposed this model, some typical values were given to all of these models without too much of a justification. So to evaluate this model, what we've done is we've performed a suite of LES simulations divided into 3 sets, A, B, and C. We've adjusted these input parameters so that we get the same velocity at the hub height, around 25 in non-dimensional units, and different turbulence intensity. So all these cases here have an incoming turbulence intensity of 12%. All these cases have 8%, all these cases have 6%. And by adjusting the input parameters in this way, and maintaining the same velocity and the same 3 different levels of turbulence intensity, what we achieve is we achieve different shears, there are different values of vertical shear, and different values of the incoming streamwise integral length scale. And so this allows us to isolate the effect of shear and of LUX, of the integral length scale of the inflow turbulence. and study the effect of that on the wind turbine wake evolution. So this is the same result that was shown in the previous slide. This is my inflow. I have 5 cases under set A, all of them with the same incoming velocity at the hub height and the same turbulence intensity at the hub height of 12%. Similarly, set B has 8% and set C has 6%. But as you can see, they have different shear levels, different DUDZ values essentially in each cases of each set. So this is what the baseline model prediction looks like against the LES for selected cases. So you can see that for set A, the agreement between the model and the predictions is pretty good. It becomes progressively worse as you go to lower and lower values of ambient turbulence intensity. So what this points to is, at the very least, that not that the model should be improved, but at the very least that the parameters need to be tuned correctly. And of course, even if parameter tuning fails, then you need to improve the model as well. So before tuning the model, before tuning the parameters, we study sensitivity of the parameter of the model to all the 3 parameters. So what we've done is we've used uncertainty quantification using polynomial chaos expansions. So some of you may know this, some of you may not. What you do is you essentially expand or write an expansion of your unknown quantity. The unknown quantity or your output wave quantity here is sigma, which is the wake width. It's a function of x, the downstream distance, as well as 3 parameters, which are put into this vector psi. So this vector psi has the 3 parameters that are uncertain, and you write this as an expansion. The basis functions psi are typically taken from some family of orthogonal polynomials, and the functional form for psi that you select depends on what the PDF of the uncertain variable is. So for example, if your uncertain variable is the PDF is a Gaussian, then you would use Hermite polynomials. In our case, our uncertain variables are taken to be uniformly distributed, so we use legendary polynomials. So once you have the expansion, the coefficients of this expansion, aijk in this case, can be calculated simply putting the expansion onto the orthogonal basis. So essentially, you take inner products, and because of the orthogonality, you can get, you don't have to solve a system of linear equations. You can directly get each coefficient individually. The angle braces here denote an inner product, and what you can see is the denominator is analytic. Once you select a family of orthogonal polynomials, you can write down the denominator analytically. The numerator needs to be computed numerically because this sigma comes from our model. And that integration can be done using any quadrature, say Newton cotes or Gauss quadrature. So once the UQ coefficients are known, once the aijk's are known, you now have a surrogate model for your wake width sigma. And so you can then query that model for intermediate values of your parameters, or of the uncertain parameters. You can use that to reconstruct the entire PDF, take different moments of that PDF, and so on. And you can also compute what are called Sobol indices, which quantify the relative contribution to the variance of the output because of individual uncertain parameters. So for example, the first order Sobol index is defined in this way. What is the variance in sigma because of variance in psi m divided by the total variance? And similarly, you can define the second order and the third order Sobol indices as well. All right, so we've done that, and CFD-based Sobol sensitivity analysis using the UQLab package. And assume uniform distribution for all the coefficients, and what goes well with that is to use legendary polynomials for your basis functions. And what we see is, you see some of the results here. So these are our LES results. There is now, you don't have one prediction for the output of the model output. You have a mean, and then you have a band of predictions, right? So you have the mean, and then you have a lower band and an upper band given by 1 sigma of the input parameters. So what you see is all your predictions are uncertain. the uncertainty generally increases as you go further downstream from the turbine. You can see that this band is expanding in its width. So if we look closely at one of these bands, what you find is you can draw the mean and you can draw the variance because of each individual input parameter separately. So if you look closely, what you'll find is this plus minus sigma because of gamma, or if gamma is varied by 1 standard deviation around its mean, the difference that causes in the output is larger than the difference caused by 1 standard deviation variance in any of the other inflow parameters. And not for followed by for S prime. This is further quantified using sensitivity indices for all our for multiple cases at different x by d locations. So what you can see is generally Sobol index for gamma is the largest, followed by the Sobol index for S prime, which is the mixing layer spreading rate. And for lower values of Ti, that is in set C, what you see is in the close to the turbine, S prime is the most sensitive parameter. And after a certain distance, gamma again becomes the most sensitive parameter. So what all this suggests is overall, I mean, if I were to just look at this picture, gamma is the most sensitive parameter, and that is what I should focus my attention on. I should try to tune gamma to get better model predictions. That's what it was. So it's crucial to determine gamma accurately. So we look at the gamma parameter a little more closely. So I'm now coming to the flow physics for the next few minutes. So we look at the gamma parameter a little closely. What is that? That is essentially the Lagrangian to Eulerian timescale ratio parameter. So if you have the Lagrangian integral timescale divided by the Eulerian integral timescale, that is assumed to be proportional to 1 over IV, which is the transverse streamwise intensity, with this proportionality constant of gamma. So what we've done is we've used our LES data to calculate gamma from its definition itself. And so for that purpose, we introduced multiple Eulerian probes, which are nothing but stationary probes in your CFD simulation. And we also introduced some Lagrangian probes, which is nothing but particles, massless tracer particles that are injected at different locations in the flow and allowed to advect downstream. So we use multiple Eulerian and Lagrangian probes in the wake. These are some particle trajectories that you see. And from these, we get multiple time series. From these time series, we can calculate different statistics. So these are the Eulerian statistics. These are the Lagrangian statistics. This is quantified in terms of the streamwise, transverse turbulence intensity, IV, expressed as a percentage. So this is the PDF of IV from the Eulerian probes and from the Lagrangian probes, and the timescales that are the integral timescales computed from those. And what we see is there is a clear scale separation between the Eulerian timescale and the Lagrangian timescale. If we take a ratio of these two and use that to calculate gamma, what we see is gamma as a function of turbulence intensity is not constant, but it increases with IU. So as turbulence intensity increases, the gamma value also increases. And this is in contrast to what previous studies have assumed. So previous studies have implicitly assumed that constant. They've assumed different values based on different conditions, but within one simulation, they've always assumed gamma to be a constant. And which is the default value that was used by in the default parameter that in the default baseline model predictions that I showed you earlier. When we actually incorporate this, we actually make gamma as a function of the turbulence intensity. What we find is that the model predictions do improve quite a bit. As you can see here, for the lower TI cases, we see that the model approaches the LES predictions better than it did earlier. Of course, there is still scope for further improvement, as we saw in this case, for example, the S prime parameter, the spreading rate parameter, was also had a significant impact on the results, and so so there is scope for improving, for doing something here as well. So that brings me to the last thing that I want to talk about, which is our baby steps in using pins for flow reconstruction. All know this. There is an input layer, then there is a layer of neurons behind that. You have the output layer. You can make predictions. From that, you can do automatic differentiation, and from that, you can impose physics losses, 3D losses, and so on. So what we've done is we've taken a turbine. We've taken the hub height, a plane along the hub height of the turbine, and we've distributed points randomly within a certain box here. And so, for example, if you have to do a RANS, you would need about 100,000 points in this plane. In a 3D simulation, you will have larger, but in this 2D plane, placed about 500 points distributed randomly in this wake, in this hub height plane. We are clubbing all of these terms, the Reynolds stress terms, essentially into one term here. This Ft is the turbine force, is that force induced by the turbine. And this is the model tells us. This is your CFD result. This is your the flow reconstructed by the pin. And there is very little error in the mean velocity, in the mean streamwise velocity, in the span-wise velocity, and in the pressure. We do see some errors here. This can be quantified further, and we can see that the mean velocity at different locations downstream is reconstructed quite accurately. Similarly, is predicted reconstructed reasonably, not so much the y in the y momentum. So, I mean, these are our baby steps. So we need to talk about generalizability, different Reynolds numbers, different thrust coefficients, different turbine parameters, and so on. So to summarize, we use high fidelity LES that allows us to understand, resolve and understand key processes accurately. I've talked about uncertainty quantification within the framework of polynomial chaos expansion-based sensitivity analysis. And in this particular example, we were able to identify the gamma parameter, Lagrangian to Eulerian timescale ratio, as a key parameter, and proposed modifications so that the model agreed better. And we started using pin for flow reconstruction. We've also done a little bit on coefficient extraction. If you have an LES data, how do you extract RANS coefficients using pins? But I wasn't able to talk about that today. So just to summarize, there are many challenges, many open questions, and a lot of things, a lot of interesting work that can be done in this field. So thank you, and I'm happy to take any questions.
Thank you, Niranjan. Questions?
Thank you, Niranjan. Excellent talk. So you talked about this 12% free stream intensity. Was that at a given location, and it varies across the boundary layer, or?
That is at the hub height. That intensity also has a profile.
Right.
This thing was at the hub height.
Okay.
Yeah. So this is the profile of the intensity.
Yeah. So that was the question that my understanding is that it's not just the intensity. You also have to worry about the eddy sizes, and so how do you decide for these wind farms? Because that would depend on the geographical location, and somebody has to give you this information. So when you do these simulations, how you choose all this? There's so much to. I mean, what is the best available models?
Right. So the simplest available model is you assume an incoming boundary layer which is fully developed. The boundary layer has a height of about between 1 and 3 kilometers. So you assume that you have a fully developed half-channel flow, so to say. The ground is flat and you have a lid at 1 kilometer or 1.5 kilometers. And so when you have that, then your velocity profile is a log law, intensity profile is a reverse log law, and so on. And these are reasonable assumptions. So at the hub height, you do see about between 8 to 12% intensity is quite frequently seen.
This would be a little bit upstream of the first turbine.
Yes. If the turbine were not present, these would be the turbines.
And how does one account for, let's say, because of the hilly area or the terrain, you would get a different eddy size? Do you account for that, or you?
So because the inflow is a precursor, we run a precursor simulation. So we have eddies of different sizes. The eddy size is proportional to the distance from the ground in this fully developed half-channel flow. And so all of that is automatically, it's incorporated into the system.
Oh, so these are all divergence-free, the inflow turbulence?
Yes, so we run a precursor.
Okay.
From the precursor is only a half-channel flow, no turbines in there. And these are profiles that you get from the precursor. And then these are applied as inflow to a domain with the turbine.
Yeah, thank you for the very interesting talk. I have a couple of questions. Firstly, you compared your results against the experimental data. So where were the experiments conducted? How were the experiments conducted? So that's the first question. And the second question is, you are using an actuator line model or disk model or whatever, right? So, and did you look at the power generated by your wind farm, right? The wind turbine farm in your simulations as a function of time?
Right. So these experiments primarily they are wind tunnel experiments. Primarily these are wind tunnel experiments because there are miniature turbines that people come up with which have kind of the same thrust coefficient, power coefficient. It's hard to have exact dynamic similarity, but people do these scaled down wind tunnel experiments, which is what we produce. Comparing with observations is very complicated. Can be done, but the wind is very rarely along one direction, so a lot of data cleanup has to be done, and to the point that it becomes almost meaningless to do comparisons to observations. Your second question was about power. So power compares pretty well, but the the electric power that you generate depends not only on this. It goes through a gearbox to a generator. The generator in an actual wind turbine, the generator also exerts load on the turbine. So the actual RPM of the turbine is dependent on the generator load as well. So we don't get into that. That can be done, but we don't get into that. So the matching power exactly is not. Yes. So they do measure the power, and if you can match the conditions exactly of the generator and the load exerted back by the generator on the it also goes through a torque controlling algorithm. There is a controller that controls the torque and which again feeds back into the RPM of the turbine. So if you do all of that will match. It's a different dynamical system actually.
Sure. Yeah. Thank you.
Thank you for the full package talk from physics to engineering. So my question is, one of the key parameters is the turbulent Schmidt number. So that's included because of the atmospheric boundary layer temperature stratification, or is it something else?
So the Schmidt number is so that particular part of the wake width tries to quantify effects of ambient turbulence. And so if the ambient turbulence
but
is...
you also have some diffusivity coefficient, right? Eddy in the Schmidt number definition, SC.
Yes.
T.
So this is the Schmidt number, and this is the fluctuating transverse velocity filtered at a certain scale. So this entire term is effect of ambient turbulence.
Yes.
And it turns out that this Schmidt number has very little effect on the numerical value has very little effect on the model.
Yeah, I was wondering
whether you use
it is
0.5 or 0.7 doesn't make.
I was wondering whether it was coming from the stratification of the atmospheric boundary layer.
So these are neutral. But when you, yeah, I mean the Schmidt number will change when you change stratification. So perhaps that will become important under convective versus.
And also for Kanpur weather where you have a lot of fog, right? The stratification inspired by today morning. You can look at those effects.
Yes.
Thank you.
We don't have wind turbines.
But you do have ambient turbulence.
Okay, thanks for the nice talk. Actually, that question is not the main part of your talk, but I also interested in the incoming flow turbulence. And incoming turbulence is strongly affected by the stratification as well as the roughness. And we would like to control these parameters for the incoming flow. I'd like to know how you generate the incoming turbulence. You use half-channel flow simulation?
Yes.
And the half-channel simulations, and also you change the stratifications and also roughness. How you model the roughness?
So we are not focusing on stratification at all in this particular work. So we just have a neutral half channel.
Okay.
If you want to do stratified simulations, you can do you can have a pressure gradient driven flow with stratification and with an inversion height. The roughness, so the close to the wall, we do wall modeling, and so the surface is, I mean we have an aerodynamic surface roughness. So the roughness or the stress imposed is parameterized by a Z naught.
Okay. For the half-channel flow, use the periodic boundary conditions, right?
Yes.
But in that case, you impose the stable stratifications. Maybe flow become a laminar. It's different from the spatial development boundary layers.
Yes.
So we need some smart way. It's necessary, I think.
Yes. In stable boundary layers with higher stability, you need larger domains, and
it's a bit tricky.
It can become laminar.
Yeah.
Anikesh is an expert in that.
Sure. So Niranjan, the simulation that you were showing, the turbines are rotating or not?
So these are actuator disk simulations. So we have effect of rotation, but we don't individually resolve every blade. We impose body forces, both tangential, normal and tangential, in the entire disk.
But you can, so the immersed boundary, so it's a sharp interface method, right?
Yes.
So rotation you could do, or that's not there yet?
But immersed boundary is not used for the turbines.
Okay, all right. Okay, so if there is no questions, we should take a break, tea break, and then we'll come back in 15 minutes. Thank you, Niranjan. Okay, so we are back. Okay, so welcome back. So our next speaker is Dr. Rajesh Ranjan. So Rajesh graduated from JNCSR, and then he has been in Ohio State, the Ohio State University. So Rajesh works on developing high-fidelity computational methods and data-driven approaches for aerospace and mechanical engineering applications. And today he's going to talk about data-driven pins for shock-dominated flows and SWBL, BL, BLIS.
Okay, there are
So, Rajesh.
Yeah, just give me a minute, I think this. Hello. Okay, so 20 minutes I'm going to tell you a story, and these are of that story. So I'm going to talk about a little bit about the beautiful and the precise CFD, because as many of you might be knowing, I'm basically a CFD person to develop codes which I did in my PhD and doing the postdoc also. And then the question is, why did I shift to pin? Okay, and okay, if we heard many talks about pin, and we saw that you can actually do the thing that you are doing with CFD with pin also. When I say CFD is low random number, I mean, and without any data you can use pin to get those things which Dr. Jonia was also showing. Okay, then the question is, does it work? What about compressible flows, especially with SOX? And then what next? So that's the chapters of the story. Let's see how much I can complete. Okay, so these are some of the works that I've been doing. One is in vortex dynamics. If you look at any military cargo aircraft, okay, you will have very high upsweep, and because of this upsweep, you will have basically this vortices which will form on the upswept body. And if you'd like to simulate that, you will have to use approaches like LES and DNS, and this is how you would you see very large vortices, okay, and then you have smaller structures around that. You can do a lot of analysis here. You can basically look at the instability here. Okay, you can find out the inherent modes. You can do POD, DMDR. We have done all those things, and they are published. I'll not spend too much time there. Okay, we have also tried, like, if you do different angles. So if you look at 20 degree, there are strong vortices. Okay, when you go to higher upsweep angle like 45 degree, they become like a wake. Okay, the separation region becomes very, very big. And they all have basically their own advantages and disadvantages. Okay, here the drag is due to the wake region, here it is due to the strong vortices. You don't want to be in either this or this, but you have to have a ramp because you have to basically drop the baggages. Right, so we did some analysis. This was for Air Force Office of Scientific Research. We wanted to find out what is the optimal angle that we can use for this aircraft. Then I also have interest in turbo machinery. So let's say if I want to get this turbine blade, and here the interest is more like fundamental. What happens to the transition length when you have FSTI and no FSTI? So if there is no free stream turbulence, Okay, so then you will have structures like this. The separation, the transition is purely separation induced. Okay, and this is the separation length that you can see, and you can see this is laminar, and then it becomes transitional, and ultimately you have smaller structures which form. So this is simulated using the code that I developed in my PhD. It's an unstructured based code, mesh-based code. This is called Anuroop. And you can see those vertices, basically you can track those vertices for a very, very long time. If you go for 10% free stream turbulence, so here we do a pre-compute a box turbulence, and we put it in front of this inflow, okay, and we manipulate the intensity the way you want. And you can see that now you have a lot of structures here due to the turbulence, and the separation region becomes much smaller, okay, which you can see in this plot, okay, and which is expected. Okay, so this was to, and if you try to trace the vertices, basically they break down much early, and that's why the separation region is smaller here. Okay, so which is what is expected. Then I also work in the area of compressible turbulence. So the interest here is that we know the Kolmogorov famous law that k to the minus 5/3 in an inertial range. And what happens when the turbulence is compressible? That means I'm talking about the turbulent Mach number. If it goes beyond, let's say 1, 2, or 3, does this law hold, or do you have change in scales? And also, how is the energy transfer between fluxes from compressible to basically incompressible? Right, so this is simulation done using the Prabha code, and this is a turbulent Mach number of 3. And you can see a lot of formation of these shocklets, and there's an energy transfer between the vertical scales and the thermal energy, okay, through the Peiser dilatation term. And if you look at the scaling here, so this is at Mach 1.4, and the red one is basically the rotational or the incompressible part. The green one is the compressible part, and this is the total one, okay, EU. And normally it's minus 5/3. So if you do in incompressible or maybe subsonic flow, you get minus 1.66, which is around minus 5/3. So as you increase the compressibility, it goes from minus 1.66 to all the way to minus 2, okay, at 3, and it can become even more shallower. Okay, so that's what happens because the energy gets transferred from the rotational mode to the mode with the divergence, the compressible mode. Okay, so that's what we notice here, that it becomes shallower. And on the other hand, the EC spectrum, which was normally in the Burgers turbulence, is minus 2, and it basically goes minus 1.2 and all, okay, 1.82. And then I do a little bit of hypersonics. Okay, so this is another code, Prabha. So I have basically 3 codes. One is Prabha, which is a finite difference curvilinear code. Dhara, which is purely finite difference, but we have Venu and Tino kind of schemes. And then Anuroop, which is unstructured grid-based code. Okay, so if you look at any scramjet, you have these double lamps, which gives you the external compression. Okay, and the interest here was like most of the simulation that you see in the literature, they are basically 2-dimensional, and we wanted to see for this ramp, which is the aft angle is 55 degree, whether the flow is 2-dimensional. Okay, so we did 3-dimensional simulation, and we can do 3-dimensional because all those codes are converted to GPUs. They all run on GPU, and what used to take maybe months, now we can do in maybe few hours, okay, with these codes. And you can see there are some differences between 2D and 3D here. Okay, and what we did the simulation for 45-degree ramp, the second ramp angle, and the 55-degree ramp. And we see up to 45 degrees, it's 2-dimensional everywhere. This is the span-wise distance. Okay, but as you go to higher angles like 55 degree, it is essential to do 3-dimensional simulations. We have also done some curvature effect. What if you smooth the curvature here? Okay, so I'll not go into those details. That will be for another day. And then I have some interest in turbulence modeling, okay, to improve the turbulence model, to tune it, to capture flows, like capture the wake region more appropriately, even model the SWI, the unstart phenomena, the propeller modeling. So if you have a propeller in front of the wing, how do you basically account for the change in the shape, the optimal shape due to the propeller? Okay, and then something on, let's say you have shock and expansion very close by. So how do you improve the Reynolds number, the turbulence model to basically improve the predictions? And also some fundamental work like in flat transitions. I'm working on trying to tune the model and perhaps propose a new model which can do this predictions much better. Okay. So far so good, because I hope I convince you that I do a broad range of CFD from very low Mach number to high Mach number. Then why pin? We can do most of the things using CFD. So the question, so if you, I was working on a problem by GTRE, DRDO, and they gave a turbine blade, which is a small turbofan engine, a high pressure turbine blade. And these are the points that they have given me. Okay, these are the experimental points that you see here. Okay, this is the only information that they had. Okay, I asked whether you measured skin friction. They said no. I asked, do you know where if there is a separation on the suction side? They said, oh, we don't have any information. This is the only measurement they have. Okay, so then of course we did some DNS, and we found that okay, if the grid is coarse, you will get this. If you sufficiently refine it, probably will match the experiment, right? But we had no other information apart from this the pressure probe points that you have on the body. That was one thing. Secondly, when we did with different turbulence models, okay, SST, RKE, then we had some DES kind of model also. They also had basically the predictions which are very far from the blade that you have from the experiment, right? So we wanted to have a technology which can take very few data on the blade, maybe some probe measurements, some pressure measurements, and you pass it through a black box and give me the entire flow field. So it should respect the data points that you have here on the blade. Okay, it should exactly match there. At the same time, it should also give me the shear stress, the separation region, and everything that I want. Okay, so in CFD, you do the simulation and try to match it with the experimental data. You do the grid convergence if it does not match, or maybe the change the turbulence model. But can I have an approach where I say that okay, these are the points which I need to satisfy, and apart from that, satisfy the governing equations and give me the entire solution, right? So that's where the motivation was. And the second thing was, of course, I wanted to tune the turbulence model so that the weak profiles become better, and the machine learning comes a natural approach. So I also work with some experiment list, and they have this TOMO PIV kind of thing. Okay, can we basically improve the resolution that we have using machine learning? So that's another interest. And I think these kind of things have been spoken earlier also. You have a range data, can you add small scales there and make it LES using machine learning? Okay, so that's where I started using neural network. Okay, because that was the most advanced, that is the most advanced deep learning approach as of now. So I'll not go into detail. So basically, you have some true value, some prediction, and you take the L2 error of that, and you try to train. And basically, it's an optimization problem rather than it's a problem what you do in sequential solver in CFD. Okay, because the number of parameters are very, very high, the W is very, very high, and the number of equations are small. Okay, so it's an optimization problem. So if you do this, let's say I'm trying to solve a simple harmonic motion kind of problem, and I know that these are the points, these are the measurements that I have, and if I try to use a neural network through this by taking the loss function as in neural network minus the true value, and if you do that, this is what you will get. Okay, so ultimately it will fit very well in this region, but then it will basically make a big mistake, or the error will be very high in this particular region, right? But as I was trying to convince you that we have very few measurements in our data sets. Okay, so can we have like only these measurements, but still try to find out what is happening here, right? So the governing equations comes to our rescue. So let's say if you know these governing equations, okay, so we can fit in these governing equations as one of the losses. This is the data loss, and this is the PD loss. And if you have boundary condition, initial condition, you can put those also. And if you do the same thing here, okay, so it starts with that initial condition, and you can see that it fits well. So that is the advantages of using physics in data, particularly for the CFD community where we don't have enough data. If you are trying to do image processing or maybe like ChatGPT, you have a lot of data available, but for CFD, if you want reliable data, there are only handful. Okay, so can we use those data to basically make a good prediction? And that's where the PD comes into picture. And if you, for this example, let's say I have these red points. I don't know if you can see that. They are the basically points coming from the data set, maybe some experiment. Okay, and if you just use without physics, this is what you're going to get. It is going to satisfy every point on the red point, but then it will mess up the entire other flow field. If you just introduce physics there, this is how you will get for the same condition. right? So with that spirit, we start with the pin, okay? But qualitatively looks good, but does it work, right? So for a practical problem, because we are interested in accuracy, whether the CP matches and all those kind of things. So this is mainly done by Prashant and also some contribution from Aditya and Malvika. Okay, so this is how we're going to do for the fluid dynamical problem. So if you have space and time, here x can be x, y, or if it is 3D, then x, y, z, and the time, so they are all solved together. We pass it through this neural network, okay, and then the output variables are basically rho, u, and the velocities, okay, because we mostly do compressible. We have done some incompressible also, I'll show that. And then you have autograd function that can give you all the gradients, and then you have all these losses, and finally your output is basically this the flow on in the domain. Okay. So this is for the lead driven cavity. Okay. So we did for RE equal to 100, 1000, and 3200, and this is purely data free. There is no data here, and it actually matches pretty well, and you can see one-to-one comparison between CFD and pin. Okay. So that's a very canonical problem. You can also do the flow past an aerofoil, and again you can see runoff number is very, very low. The advantage here is that if you are going to do CFD, you might have to make a grid like this. Okay, in pin you can just distribute your points, okay, like a cloud, and you can see the accuracy is quite good in this case also. Even the match of CP and at different angles of attack. Okay, so there is no grid generation process involved here. So that is another advantage of pin. Okay, even the flow past a cylinder. So I think Dr. Junia, she talked in the morning. So we were able to predict the vortex shading as well as, I mean, of course this is a simple profile, but here also we don't have any grid or anything, and we are able to, so these are some baby steps just to show that pin can do job even without data. If you add data, it becomes better, okay, the optimization path becomes more clear, and it will not be stuck into some local minima and all, you will get the global minima. But let's see, if you don't have any data, can we make this prediction? So that was the challenge. And also for the turbomotion flows also, we got basically pretty good distribution. And this is at low runoff number around RE equal to 1000. We want to basically make it work for higher turbulence, I mean higher runoff number and all. So that is the work that we are doing. But before going that, we are working on this blade is called a spleen blade, and we have got shocks on these blades. So the task was whether the pin can predict shocks. Okay. So yeah, so that's the thing. What about the compressible flows? So we started doing with the short shock tube, which is a standard problem, the high pressure and low pressure. Again, we are not using any data. Okay, so this is the condition given by Gary Sword. Okay, and you have these shocks which will move on the right and expansion fan which will move on the left. Okay, so when we started with the vanilla pin, okay, no data, and this is what our results are. Okay, and you can see that the shock region is not predicted at all. I mean, it tries to basically follow the path, I mean follow the profile, but it misses badly. And the main question here, the main concern is that when you try to use pin, so it's a global approach, and what it does is that whenever there is a shock, there is a high gradient, okay, and whenever there is a high gradient, the network tries to think that it's an error, and it tries to modify the weight there. So it tries to smooth out, it does not understand that it's a physical phenomena. Okay, and that's why it's an ill-poised optimization at the discontinuity, and that's why you get this kind of solution. Of course, there are issues of spectral bias. It resolves the low frequency better than high frequency. It does not have the numerical dissipation, so it does not know whether there will be a shock here or expansion here, because there is no entropy equation here. So to basically address this, people have tried different approaches. One is that they use clustered points here. So if you know where the shock is going to form, they will use the clustered points there. They have also used this entropy inequality equation apart from the Euler equations that we have. They also use this vanishing viscosity model. Okay, so the vanishing viscosity model, they have tried with different viscosity. Okay, and this is the vanishing viscosity. That means the nu goes to 0 if there is no shock, and near the shock you will have some viscosity. Just like we are trying to mimic the artificial or numerical viscosity that we have in the numerical model. And if you use a very high viscosity, this is how you are going to get. If very low, then this is how you are going to get it. Okay, so you need to have the exact amount of viscosity to predict it better. Okay, so this is what we tried for like an oblique shock problem. So if you use entropy inequality, there's a lot of diffusion here across the sock. If you use high viscosity, this is smeared out. If you use low viscosity, then it is better. But can we have an approach where the viscosity need not be an hyperparameter? Okay, the network should be able to predict the viscosity by itself. Okay, so that's what we did. So now we change the network. We pass it through another network where the second network basically only predicts the viscosity. Okay, and the first network predicts the rho, P, U, and V. Okay, so we actually tried new with this network also, but the challenge here is that there is a lot of separation of scales. The viscosity value is very, very small. We are solving non-dimensional equations, so they are all of the range 1, around 1, order 1, and this is basically 10 to the minus 3, minus 4. So if you use in the same network, the viscosity that they will get will be probably a bit higher than what you would expect. Okay, so we did it for the short sock tube, and you can see the predictions have become much better now. And the good thing about PIN that you can get all the solution, all the time solution at one time, and this is for 0.2 second. It matches pretty well. And you can see that you can start with any viscosity in the beginning, initial condition, still converges to the same value which the network wants to take for the sock. And these are the convergence of this, and we can go to convergence for 10 to the minus 5 or minus 6. And this is the comparison. So we have taken the row scheme, the blue one, and the analytical solution. Then we have basically tried the global model also, where the viscosity is constant everywhere. And then we have LNN1, LNN2, which are basically the neural network 1, and the viscosity is a part of the same neural network, or viscosity is a separate neural network. And we observe that this LNN2, which is the red one here or here, they are basically much closer to the CFD solution compared to all other approaches. The other advantage of local is that, let's say, if the sock and expansion fan both present in your system, so it can switch off near the expansion fan, and it can switch on near the sock. So that is also done. Okay, this we discussed already. We tried with the lax sock tube, and there also it works fine. Okay, and we have tried many different cases, and it works fine. Even the compression corner, expansion corner, and the predictions of the pin without any data is closer to like theoretical as well as the numerical approaches. Okay, and then we tried with 2D domain problem also. So we have basically 4 different quadrants, and you can give the values of rho, U, V, P in different quadrants to have maybe 4 socks or 4 expansion fan, or 2 socks, 2 discontinuities, or 4 discontinuities kind of thing. Okay, and these are the values given there. And this is basically one configuration where there are 4 contact discontinuities. This is from CFD, and this is when you use a global model, and this is when you use the local model. And you can see the predictions are basically much close to CFD here. Similarly, when there are 4 socks, there are 1, 2, 3, 4, there are 4 socks here. And of course, this is slightly smeared out compared to what you have here, but still it is going towards that path. And this is, so this is again a different configuration, and here also the predictions are quite close to what you have there. Okay, so this is one thing I want to tell you, that if you have an expansion corner, the viscosity automatically converges to 0, so you don't need any viscosity there. But if you have compression corner, and if depending on the configuration, it adjusts to the viscosity, which is the minimum required viscosity to resolve the sock. So this is fully automated. You don't need to give any manual input there. So with that, we become a little bit ambitious, and we wanted to see whether the pin can resolve the Bondiel error, okay, the sock Bondiel interaction. Right. So now these are the equations we are solving. This is no longer the Euler equation, and you have the Reynolds number, which is coming as a parameter. Okay. And the problem here is, as I told you, it's an optimization problem. If all are of same scales, then it can handle very well. But now as the Reynolds number increases, the 1 by RE becomes smaller and smaller. It can go to 10 by minus 6 and all. So then it becomes very, very small number, and the convergence is a big problem there. And that is why the pin is not very successful yet for the turbulence problems. Okay. So we tried with the compression corner. So these are some representative images from our LES simulations. Okay, these are not necessarily related to this. This is a 10 degree we are trying to solve, and Reynolds number of 16,800, and Mach is 3.0. So how are you going to solve, because the Reynolds number is around 70,000, so 1 by RE is very, very small number. So what we did Reynolds number ramping. So we started with inviscid flow. We started increasing Reynolds number slowly. So if you look at here, so this is R equal to 0, and then we start basically changing Reynolds number slowly. Okay, so we ramp it up after every, let's say, 1000 epochs, we ramp it to R equal to 1000 to 2000 to 3000 to 4000, and you can see that you are able to predict this separation region here. Okay, and this is the first simulation I think we have performed. I mean, the first prediction using pin. I have not seen this kind of result in the literature so far. Okay, and these are the basically comparison between CFD and pin for the same case, 16,800 and Mach equal to 3. Okay, so this shows that pin is slowly moving towards what you are expecting from CFD. Of course, it is much more expensive than CFD as of now. Okay, but still with the kind of GPUs that we have, we can actually make it reasonably fast. Okay, so right now it takes around 4 or 5 hours to get to this Reynolds number. Okay, turbulence is another issue that we have not looked at in detail unless we have some data points. But for this kind of problems, we have addressed it. Similarly, for shock-molecular interactions, let's say you have a shock which is impinging on a flat plate, and you have this separation which is developing here with time. Okay, and then you have expansion fan, reattachment shock, and everything. So this is using our CFD code. We wanted to see whether the pin can do the same thing. Okay, so that's what we did. We actually mimic the bonding condition that we had in CFD, slip condition, no slip, and adiabatic, and this is the inflow, and then you have the shock impinging from the top, and these are the results that you are getting from our pin. Okay, again it is data free completely. If you add some data, it will actually become better. Okay, so this is the left one is CFD and right one is pin, and you can see that the prediction of the separation bubble is basically smaller in pin compared to what you get from the CFD. Okay, but we are getting there. There are a lot of things that can be done in this to improve the accuracy. One thing we observed that the one-to-one map of the bonding condition between the CFD will not work for pin. We also looked at the hard constant versus soft constant. Okay, so sometimes the soft constant is better than the hard constant. So those are the things that we're looking at. So this is the end of the story. So what next? So this is what we saw, that these are the advantages of pin. So this is mesh free. It can use to enrich the experimental data set. Okay, it can help in the super resolution, inverse problems. I think some people talked about this. Okay, improving the turbulence models, the tuning of the parameter, and one important thing, the self optimization. So once you basically train the network, and what Dr. Junia was showing in the morning, that you can use basically DeepONet kind of configuration where there is a separate network where you can have the parameter, the shape parameter as a separate network, and you don't have to train it again and again, and it can do a good job here. Okay, so yeah, and there are some limitations, of course, as we discussed since yesterday. The instability and cost it is more expensive. It has poor accuracy in stiff problems and high Reynolds number flows, very sensitive to hyperparameter. Bonding condition is not yet clear. See, spin is here for last maybe 4 or 5 years. The CFD has been there for 60, 70 years. But I think the development is very, very fast. Okay, there are many groups working on this. Okay, and there are challenges in scalability and all, so that we are trying to see now. So with that, I would like to thank you for your patient listening, and I'll be happy to take questions. Thank you.
Right, thanks, Rajesh. Questions?
Hi, Rajesh.
Yeah.
Thanks. Glad that you have not stopped at a certain point and went into more complicated cases.
Yeah.
So my question is, in all of these pins architecture, I'm assuming that you have used CNNs and simple architectures, right?
No, this is not CNN. This is fully connected.
Fully connected.
Yeah.
But these are still simple. So why don't we see more complex architectures like transformers or something like that, penetrating into the scientific computing like fluid dynamics as prominently as it has done in other
See,
cases?
depending on, I mean, we have also tried using transformer in some of the problems. Okay, but depending on what task you have, like for example, if you want to more interested in images, okay, then maybe CNN is a better way. Okay, if you are into large language models and all, I think the transformers is a better way. Okay, but here we want to have a mapping between the inflow and outflow, and every region important. Okay. So So if you have probably, let's say, huge separation in the boundary layer and the external flow, then maybe, see, another thing is that for those cases you require a lot of data.
Yes.
Okay, here I'm trying to approach this problem from a data-free manner. Okay, so there is no data involved anywhere here. So this is, right now, what we're trying to do is that can we address complex problems using pin without using any data. Okay, so that is the approach till now. Okay, ultimately, let's say the GTA people come to me and tell me that these are the measurements that I have. I can fit in the pin, and I will say that the data loss should be minimum. You can have little bit loss in physics or the boundary condition, but it should exactly match on those points.
Right.
Okay, so then probably I can trust the results that okay, whatever shear stress I'm getting or whatever heat transfer coefficient I'm getting will be accurate because it is matching the data values there. Okay, so that's yeah.
Very good talk. Thanks for the very nice talk. So the question of grid convergence, right, that often comes up in the context of PIN. I just wanted to, because you've applied it in so many different complex cases, what has been your experience with putting the points? Like I saw in the airfoil case, you've tried to cluster it more near the wall.
Yes.
In case of shocks also, did you try to cluster more? Or
No.
is it a pre-decided thing, or can you adapt it? Does it, like, is the network sensitive to it? I'm just curious
so the
about
grid conversion, as we talk in CFD, will not work here. Okay, because it's an optimization problem. It may so happen that you increase the number of grid points, but it got stuck into a local minima, and it gave you completely different solution. Okay, but having said that, you have to respect the physics of the flow that is happening there. So if there are more phenomena happening in certain region, you should have more number of grid points. Okay, if you can afford and put more collocation points everywhere, then it is good. So in this case, for example, sock modulated interactions and all, we have not put any clustering or anything because the grid, I mean the sock is evolving. So you cannot fix it at given point. And automatically by adjusting the viscosity or the 1/RA parameter, it is basically adjusting to that thing. Right, so that is something that you're looking at. Can we make it basically responding to the number of collocation points that you have, right? So can we say that, okay, now we have increased the number of points, so it is more accurate. But we are not into that stage as of now.
Okay, and one last thing. So at this stage, the way you're doing the pins, it is dependent on the particular, so if you train it for a particular geometry, and you change the geometry, you have to retrain it, right?
Yes, as of now, yes. But
And
we have actually more or less fixed the how we want to distribute the hyperparameters.
Okay.
Okay, so we will have a paper maybe coming up next month. So for, I mean, basically what kind of activation function you want to use, or how do you basically change the learning rate, okay, and how to distribute the collocation points, how to standardize the domain and all those things. So, and what kind of optimizer you can use for that kind of problems. So all of those are basically finalized. So we use all of this together, but we have to change the domain, as you rightly said, and the flow condition.
So if you compare because your solver is also on GPUs, maybe it's a direct comparison. If you compare the cost of training a new geometry from scratch and then running it versus the CFD on the GPUs, how does that compare?
No, it is very expensive compared to CFD as of now.
As of now, okay.
Yeah, the reason for that is, let's say you want to solve a 3D problem, then you have 4 dimensions. The time also gets solved at the same time, right? So that is a major problem here. Okay, in CFD you do time marching, right? So you don't have to store so many things at a given time. So here you have to store everything. So right now it is more expensive, but what I can say that it is more expensive, but it is not like exorbitantly or something that you cannot do, right? So you can do it. For example, the movie that you saw, I asked Prasant to make a movie of that. He ran the simulation again. We got it in 5-6 hours, the entire sub-modular interaction that we had with 800 GPU, right? So we have now powerful GPUs, so they are basically tangible. I mean, we can track it. Okay.
Okay. Thank you.
Yeah, thanks for the very interesting talk. I just wonder, like in all your simulations, even say on the turbine simulations, have you looked at the CF variations?
Yes.
Skin friction variations and the wake losses, and how good were these pins predicting because you showed CP. CP is more like an inviscid thing, right? So CP is easy to match.
No, so
but
wake loss, see, even with the turbulence model, we are not able to get the correct wake loss.
Yeah.
Okay.
But a back-to-back comparison in general.
So we have done that. I can show you maybe later.
Sure.
But for pin, we have not gone up to, like, say, realistic runoff number of 50,000 or 100,000 for a LPT.
Yeah.
So this is all baby steps. We are trying to see one thing at a time. So we now have method to simulate the or the predict the shock.
Yeah.
Then we have the turbine. We have basically, it took some time to fix the periodic bonding condition also in pin. It was not trivial. So now we have all the recipes at place. Now we have to impose the turbulence model, and then we have to see whether the predictions are okay compared to what you get.
It need not be turbulence model. Like you have laminar flow, right? Low Reynolds number, but even in that low Reynolds number, like was it good enough? You know, like was the agreement good enough? Is what my question is.
Okay, so no, right now we have not compared it.
Okay,
yeah.
Right. Yeah. Thank you.
Yeah, thank you.
Pradeep, done. This is all 2D.
This is all 2D. The pins are all 2D, but simulations are 3D. The CFD simulations are 3D.
So if I give you a like flow past test sphere turbulent flow data, you run it for a very long time, you can predict the turbulent flow field.
So right now I can only do the RANs, okay, or maybe I can predict some overall parameter.
Yeah.
You ask me to predict the structures and all, we cannot do that.
Like so say I give you a DNS data, right? Like a 3D data set, and because you are just doing pins and is basically the optimization function or the loss function should be like the Navier-Stokes equation, right?
Yes.
So as you said in the that GTRE problem, you have certain data points,
yeah,
but they are very low in number.
Correct.
For DNS, I give you, I don't know, millions of data sets, data points, basically the velocity, field pressure, and all.
Yeah.
So is it doable? Like provided you have very powerful GPUs.
So depending on what question you ask, let's say you give me a 1,000 snapshot, and you want to predict the 1,001 snapshot. So I don't even need pin there. I can just do a neural network and I can do that.
I'm saying like the velocity field that, so you showed that in the 2D flow past cylinder you are showing that it was evolving in time.
Yes.
Now I want evolution in time. If I give you a million data points at different time steps and all, would this be able to predict?
It will take a very, very long time, but I think it should be.
If you have very powerful GPUs,
maybe
there is a possibility.
There is a possibility, yeah.
Okay, great. Okay, thanks, Rajesh. Yeah. Let's thank the speaker again. So our next speaker is Dr. Sangwon Kim, and he has graduated from Hokkaido University, Japan. Right now, he is a postdoctoral researcher at the Center for Computational Science, Riken. And he's going to talk about time-stepping Hamiltonian simulations for Alan Kahn phase field model via quantum classical hybrid approach. Sangwon?
It's okay? So, shall we start? So, I am Sangwon Kim from Riken in Japan. So now I'm wearing the kurta in this time because it's very special chance for me to presenting for the all of the yeah. So for the presenting all of the everyone. So first I want to say namaste. Yeah, I respect God inside everyone's, and this is very special. So actually, it's the third year I visit here. So first year I visit the Professor Rao's home and went to see that there is a shrine, there is a Shiva cat, and then other gods. So I'm very impressed. And last year we had some very small workshop from the here in IIT Kampuru, and then today is too much personal here. I'm very nervous, but I want to, let me start the presentation from here. So actually, this one, now in this time, I want to presenting some quantum things. Is hybriding the HPC and the quantum side. I mean maybe this error is some kind of heterogeneous computing error. I mean, currently, not only just CPU or GPU, but using CPU, GPU at the same time, that kind of error is coming right now. In Japan, we are preparing the Fugaku Next for using the GPU and CPU at the same time. And then one more project there is using the quantum computer QPU to the HPC, and then now using the 3 of the processor. There is a plan, something like this. So maybe you, currently I want to say about some kind of Hamiltonian simulation results, which is very powerful, or some proper, some method to using the quantum computer. And then what we start this the study is that not just when we using the quantum computer, is that only there is some advantage for the scale of the simulation, but also there some any other advantage, some additional stuff. So recently we found that some kind of this kind of Alenkam phase speed model calculating based on the Hamiltonian simulation shows some interesting features. So I want to presenting from here, and then using both quantum and classical size. So my research field is actually not the quantum side, but actually mechanical engineering, and especially I usually doing some turbulent bubble simulation, the multi-phase flow simulation. So that kind of the simulation I usually using the incompressible solver. As you can see, incompressible solver, the algorithm is like this. When to calculating the momentum, and for the calculating the Poisson equation for the pressure part, and then one more is the scalar transport for the density field. And then each of them is quite dependent each other, so it is very hard to calculating independently each side. And another interesting is that the upper side, the momentum and Poisson side is quite close scale of the dynamics. I mean the very large, relatively large scale of the dt, the part. But in case of the scalar field, there is some, for the density field, there is some pinch up or some break up and collision. That kind of the scale is quite relatively smaller than the upper side. So it is very important to calculating this part very precisely and precisely to the calculating. So for that, so there is some several methods as we know. So both method is quite famous. I mean very simple, but it using some kind of some artificial the advection of the interface sharpening method like the Plick or any other method. This method is we using this method because it is very important to the calculating precisely and conservatively the volume of the fraction, and then that's why it needs some additional model for the surface tension model for the multiphase flow. There's another method in there. What I'm recently have the interest is the phase field method. The phase field method actually not for the multiphase flow. It may be for some material science in there. So what is the phase field method is actually it just using it calculating this part. This calculate part, this one is the chemical potential, and the chemical potential is based on the free energy term and the gradient term. So based on these, the calculating this part, it shows some kind of bubble or some pinch of shape is very naturally calculating. And if we adding the one more convection term on there, we can directly using for the multiphase flow simulation. And then there is some model like a Kahn-Hilliard or Alenkam method, depend on conservative or non-conservative method. And one of the disadvantage of this method is that it needed very small time step because of the gradient term. In case of the Kahn-Hilliard, there is a 2 Laplacian operator, so there is a dx power of the 4 in there, so which means the dt when we discretizing to where is that the time derivative one, the Courant number should be very small. So it is very difficult to use for this kind of simulation because they're using sometimes sub-scaling or some other method, or changing the modified the phase field method is usually used. But recently, I have some interest on something like this kind of exponential integrator. It is called as a matrix exponential. So one of the advantages of the matrix exponential is that for the linear part, it can be calculated exact result because the exponential of the matrix is some kind of infinite Taylor series. So compared to the other scheme, the accuracy is very high, only for the linear part. But if there is a nonlinear term, it needs some kind of additional treatment like Runge-Kutta or other part. But anyway, it's quite, when we're using this exponential matrix, it's quite stable for the large DT, and then, as you said. So I think maybe physics part or physics groups might know to using this kind of, it is very natural to using the exponential for the analytical solution. But HPC side, until when I see this one, I never know about this one because HPC doesn't write or doesn't use this kind of matrix exponential because treating the matrix quite high memory required, and then communication problem is occur. So we usually using just the financial different method to discretizing every time derivative term and the other term also. But when we checking when I checking some quantum algorithm, there is this kind of thing, the Hamiltonian simulation. What is the Hamiltonian simulation is that it calculating or solving the time-dependent Schrödinger equation, and that shape is nearly same to each other with the exponential matrix exponential, and then this one. So this of the time-dependent Schrödinger, the Hamiltonian simulation, using that Hamiltonian simulation calculating like this kind of time-dependent quantum state. That's why if we using this method, maybe we can removing this kind of the bottleneck of the higher requirement memory based on the quantum computer is naturally calculating the matrix calculation. So what we want to do is that we want to calculating this kind of our classical some PDE like some linear one or nonlinear one from the Hamiltonian simulation, which is actually calculating the Schrödinger equation. But the problem is that you can see that the Schrödinger equations one and then the classical one, it has some different shape. So it is actually naturally hard to using from the quantum computer for calculating classical system. One is that the imaginary number is existing there, and the A operator, the classical operator, is not generally nor Hermitian Hermite matrix. So what is the Hermite means that is some complex conjugate transpose is equal to the exact that one. So if the Hermite characteristic is secure, then that exponential of the matrix will be the unitary, which is the calculating from the quantum computer. So, and then other things what we want to calculating the recent quantum computer, we need some feasible for the near term of some quantum computer, which is noise is exacting in there. And then if we considering some nonlinear problem, then some linearization is needed because quantum computer is only for the linear problem. And another thing is, actually we not only just calculating the advection problem, which is unitary one, but non-unitary problems such as diffusion problem is also need to consider for the Navier-Stokes or other problem. So that's why for some nonlinear operator should be embedding as the unitary. So some additional method is needed. Another background is that how about the recent platform about quantum computer? So in case of the Japan, we have the two main projects like JHPC Quantum, which we using the Fugaku in the Kobe, and then there is one more the quantum computer IBM Kobe, and then in Waco place there is the RQSys the superconducting quantum computer A, and then the Ion Traps the Quantinuum computers are located, and then this project is mainly considering both computer using hybrid at the same time. Another is that in the AIST in Japan also, they also doing similar thing, and they are they have some GPU cluster and then setting or setting the quantum computer beside of them, and they want also doing some things, some hybrid things, quantum and the super HPC. So how about the global trend? It is that, maybe you have the question, it is only the Japan, but no. Actually, when we visit the SC25 in St. Louis in this time, we see that a lot of some America or Australia or some Europe group in HPC group also considering and setting some platform both using the hybrid system. And actually, this is me and Oni-san and Taki-san. So we got some best research poster award from there. Actually, we presenting the same some contents from there. So what I want to say here is that actually the HPC society also want to using both quantum computer to accelerating some calculation when calculating the main calculation is HPC. So I think this one is actually some global trend. And then when we calculating as I said before, the nonlinear PD calculating from quantum computer is a little bit difficult. So we need some linearization method like some Kahneman linearization or the von-Neumann linearization. What is doing that is that actually we have this some kind of ODE, then it extending some series of some equation, and then calculating, and then they are highly dependent on each other, and it should be extended to the infinite state of the equations. And that is also nearly similar with the Koopman-von-Neumann one. So actually this one, the original equation changing to the Liouville equation, and then if they apply the Koopman operator, it's changing as like a Schrödinger equation, and then that is also needs some infinite expansion of the equation. But actually the current quantum computer is very hard to securing all of these many number of the qubit, and then quantum computer even of course the qubit can be treating very large scale of the data, but it's finite. I mean it is not infinite. So this kind of linearization method should be truncated in somewhere. That means it will be accumulating error as over the time and time. So actually, I don't like this method because of the size and then the not feasible to the current NISQ device. And another thing is that actually this kind of the linearization method is purpose is that actually we have some zero state result, and then we're calculating the linearly, and then eventually it shows the final result. So such like some structural analysis or some material scientists, they only want to see the last one. So this kind of the linearization method may be suitable for them. But for some fluid mechanics, our side, it is important that some kind of dynamics in the middle of the calculation is important. So I think this kind of the linearization method is not so much suitable for our side. So we have this kind of the background. So what I want to hear is that personally we need some task. One is that how to transfer our classical system to the quantum side. So I'm using the Schrödingerization method, which is warped phase transform one, and that can be treating our system is from classical to the quantum side. And another thing is that also making some non-unitary operator can be making the unitary problem. So another thing is, and then another thing is that the time stepping strategy, what we usually using from the CFD side. So I don't like that kind of the Kahneman or Koopman-von-Neumann linearization. So I just stepping, and then we locally, we consider the local time step is very linear part, and then using some kind of this one. And I will talk about detail later. And there is some modification like a QFT changing to the FFT side for the Schrödingerization method, but I will talk about later. So what is the Schrödingerization? Actually, this one is some weird thing for the making our system to the quantum side. Firstly, we have to changing our PD to the OD anyway, like this shape. After then, so we sometimes our operator is not the admit, so we should decompose the A matrix operator to the H1 and H2. The equation is like this. Actually, based on this equation, the A matrix decompose to the H1 and H2, but they are admit anyway now. So our equation is like this in H1 pi and plus I H2 and pi. Then we will introducing the WAPD page. What is the WAPD page is that apply the exponential the minus p to the pi, then that will be changing to the omega equation. So we need to changing this equation to the omega equation. So arranging this equation to like this, or the derivative term for the t or p, we can get this one. And applying these three of these equation to the here, then we can changing the pi equation to the omega equation. And then one more thing is we have to need one more things here is there is no I in here. So this one, the delta p to delta omega, we will apply the Fourier transform on here. Then eventually we can get some I eta psi. I mean from the omega to psi changing. And then there is nothing changing from the other part, but only this part will be changing like this. And eventually the equation will be like this, like a Schrödinger-like equation. So we calculating from this quantum computer for the time evolution side, and then when we want to get the exact result, then we need to the inverse way. Like after evolving the result, and then inverse Fourier transform go to the inverse Fourier transform to the omega, and then when the p is equal to 0, then the exponential p will be the 1, which means the equation will be changing to the pi, and eventually we can get the already evolved result. Okay. So of course this one is maybe I think it's better here. So to do this, we need some kind of hybrid scheme. I mean, for also considering the nonlinear path. So firstly, from the pre-processing part, we have to prepare the normalizing the result, because quantum computer need to normalize the normalized data to encoding to the quantum state. And then another thing is that prepare the Hermit matrix like this. For that, and we for nonlinear terms, we calculating each time step Hermit like this. So for some kind of this one may be Burgers 1, and then this one is the Alenkant problem. So if there is some nonlinear term, it should be calculating from the classical side and then apply to the Hermit matrix and then it will be decomposed. And as I said, we are select the time stepping strategy. So actually the Hamiltonian simulation is calculating from the 0 to the exact target t. But what I want to do that here is from t to developing to the delta t only. So each time step we have to do everything like a CFD. So that's why it will be like so data is going to the quantum side and the quantum side to the classical so that's why this algorithm is actually the quantum and classical hybrid system. And then post-processing is doing preparing some quantum state for the next time step and then outputting some data. So in this time, we don't have at that time, we don't have the exact real machines account, so I using the simulator, and then it is based on the QSKIT, some framework. And then for the simulation environment, we're using the cloud system in Liken, and then based on the CPU and GPU node. And then firstly, we validate our the quantum algorithm from the linear problem. The linear problem is like this one. Then we discretizing the spatial region to the second order central differencing, and then for the time evolution, the classical side using the Runge-Kutta from the SciPy, and then using the periodic boundary condition, and the mesh resolution is 8 qubit, so 2 and 8. And then the Wapud page also needs some resolution for the exact solution, so it is the 2 and 10. So the result is actually same with each other from the on the classical side and then the quantum side, and the result is the video is like this. Another thing is that what we want to do in this time is we want to calculating the Alekhine simulation, which is nonlinear problem. So we testing the Burgos equation and the Alekhine phase field for the 1D simulation, 1D simulator. So 1D simulation, you can see that the implicit Burgos and Alekhine simulation, you can see that the result is exactly going well. And then Alekhine was, the initial condition is the cosine the distribution, and then you can see that the page is separate well beside in the middle of, and you can see the interface region is constructed well. And after that, we also testing from the 2D case. The 2D case, we just testing from the for the Alekhine simulation. So for the same time step for the classical side and then quantum side, the result is actually the initial condition is a random distribution, but same are using the same seed, so the result is actually same each other. So, but what I was checking from this, when we changing the size of the DT is increasing, and then want to see the classical side and the quantum side is difference. So when I testing from the simulator, we can see that the classical side is for the large DT is divergent, and then the calculation is it shows no error, no result. And then from the just increasing 2 times more, it shows some kind of oscillation for the high frequency one. But for the quantum algorithm, it shows very, very stable one because the exponential matrix is very stable for the only. And actually, the quantum side doesn't discretize for the time derivative term, but why the classical side is time derivative discretizing all of the term, and then the dx is 2. So that's why classical side is quickly divergent, like a page field mirror problem, because this making the DT very problem steepness. So result is like this. So I think when we using this kind of quantum computer and with this kind of specific problem, maybe we can get some more, not only the scale, not only for the advantage for the scalability, but for this kind of the accuracy and then stability can be get some additional advantage. So when we checking not only just video, when I make some graph, so the zero state is actually some specific time steps, times the result. So when there is this one, it becomes 0. So the result is actually the same at that time. So as you can see, the classical Alekhine, you can see that for the several time steps, the much more smaller one is going like this, and then eventually that shows us same result for until specific size of the DT. But when we increasing the more larger one, and is oscillating and then divergent. But on quantum side the algorithm, it shows that it reaching to the result to the exact maybe the T is maybe 4.2 around. But the quantum side is interesting is that it reached around 3.5 seconds. But I don't know why, but I think due to using the exponential matrix, I think it's quite going accurately and then reaching the exact result. But I don't know why it's much more, little bit faster than this one. So conclusion is that we established this kind of some algorithm and some framework. But the problem, what we, for the future work, actually we just get the real quantum computer account recently, so we want to calculating from there. But actually, this kind of custom gate is not is difficult to using the real computer. So we need some exact quantum circuit for this part, and then using the quantum computer and then encoding the classical data to the quantum computer is very hard to do that. So I mean the quantum state preparation is also needs some proper algorithm. And then another problem is that when we get when we pre-transfer from the outside, then we need some complex state vector, which means we need the quantum state tomography, which means that is quite expensive method currently. So I think we can, it's very hard to calculate some very large scale ones, but we will do anyway and in this year, and then want to show some next workshop on in Madras. Madras? And then another thing is it's just schematic or some just my plan. So Lican will have some two of the Grace Blackwell GPU cluster. One is for the AI, or maybe 1,600 GPU, and the quantum computer for the quantum project for the 540 GPUs Blackwell's one. That is for the algorithm, researching the algorithm or the simulating one. So it will be operating in next year. And then currently our team Cube also doing some GPU porting by the CUDA. So, and then NVIDIA also doing some kind of thing, similar thing based on the CUDA Q. So I want to make this kind of the cube to the hybriding the quantum algorithm, then want to make like a cube. The name is actually cube, same, but yeah, it's just some plan. So I don't know whether it's going well or not, but maybe you don't, you guys already knows about that. Just using the quantum algorithm is very hard to, so I want to making some test bed to clarify what kind of the problem could be occur when we using hybrid computing. So yeah, thank you for your attention. Thank you.
Thank you, Sangwon. Questions?
In CFD, we have something called as truncation error. So, like because we cannot represent real numbers with infinite precision. So, do you have such kind of errors in quantum computers as well?
You mean
truncation error? Yeah.
Truncation error. I think currently the time stepping method is quite expensive because it's going to the classical and quantum side. So I think the expected, currently we just using the simulator. So the expected error source may be from the quantum side to the classical side, the data transfer or acquiring the data from the quantum side, it should be shutting. And then it is approximated data result. So the resolution of the shot is quite depend on, it also could be the one of the error source. But I think we don't using the linear, the Kalman linearization or some linearization method. So I think that kind of the error is not included. That is my expectation.
Thank you.
Rajesh?
So you said in a classical it diverges when you increase the delta to some value, right? So there is some limitation from the quantum side also that you cannot go to arbitrary high delta t.
That is depend on the, maybe from the, when we go to the quantum side, then maybe condition number can be the one.
Okay.
Yeah.
That's why in the next plot you have it diverging, right? In the next one, if you go. Okay.
Last one is looks like going to diverge. I think more larger ones, the quantum side also could be some divergent result could be shown. So because we using the time stepping method, so if the dt is too large, then the error will be accumulated, right?
Okay. how many qubits you need to use for this?
Currently, we using 10 or 11 or 12 because we using simulator. But
Okay.
actually, over then maybe 13 or 14, the metric size will be go to terabyte or so. Yeah.
Okay.
Yeah. So that's why I want to using some QPy.
Okay.
For me, I want to using the GPU more. So yeah, currently this simulation is actually based on the CPU based one. So because I also tried the GPU environment, but I don't know why, but QSKIT from the GPU is doesn't not so much fast, and then
Yeah.
it has some weird things. So
You may use the, I think, Q quantum or the CUDA Q, either of the two,
I
because
want
they're
to alternate to because we will have the GPU cluster in next year, and then that is for the simulator. So
Okay.
that's why I want to use CUDA Q.
okay. Sure. Yeah.
So for the experiments that you have conducted in the NISQ era, what will be the time associated with the quantum state preparation versus the actual compute? Do you have any sense of?
I think is when we using the real computer, then maybe not like this clear, so it will be accumulating error on there. So actually, I have no idea about how to reducing the real computer's error. So we are now try to collaborating the one of the LICAN team member. They doing some quantum chemistry, and then they are very expert on there. So I want to ask them. Yeah, currently I don't know.
Okay.
Yeah, currently this one is actually noise-free ones because.
Yeah.
Anyway,
Yeah,
the quantum computer will be developing, and then eventually we will go to the fault tolerance quantum computer.
Yes, but my question is more on the quantum state preparation versus the execution time of manipulating the qubits. So how do they compare? Even like because you need to load the data onto the qubits.
Yeah.
And then you compute, and then you do quantum measurement. So how do
that is so right, I think. Yeah. Currently, this method is the outputting of the two, which means we have a lot of the quantum circuit, many series of the quantum circuit that will be increasing the speed. What I want to do here is that the current quantum NISQ quantum computer is very have this automatic very deeper circuit. So that's why I put out the QFD, and then we want to testing this kind of the algorithm is working well or not. So of course the speed will be decreasing, but I want to testing. So that's why it's slow, quite slow.
Okay, thank you.
So for your classical, if you can just go back to that plot, the movie. Yeah, so this one, the classical Alan Khan. So you showed that you are using this RK45, right?
This one is the Euler.
Okay.
Euler one. So I think it's more stable, right?
RK45, right?
Yeah, RK45 that is also quite steep, as I need. Is it?
Okay.
Yeah.
No, so I'm just wondering, like, as he was also asking that, quantum computer and then the time difference, right? So if you are just running it on a CPU or a GPU, although the problem that you are right now doing is of relatively lower scale, right? So if you are doing it for 3D, hopefully you'll get a much better scaling with the quantum computer. Is that so?
Anyway, thank you.
All right. So let's thank Sangwan and all the speakers and our organizers as well. So with this, we end this session and we'll be meeting after lunch. Okay, thank you.
Sir, I have an announcement to make. I thank our esteemed session chair, Professor Anikesh Pal, for effectively and smoothly handling this session. I also thank all the speakers for their insightful and engaging presentation. Now we'll have a visit to Flight Lab. Cabs are waiting outside for the speakers to pick up. Followed by the visit, the lunch is arranged at the visitor hall for speakers. Then we'll all meet for the panel discussion in the same hall by 2:30. Thank you.
whatever you decide.
So because the speaker has to leave in some time, so we'll start a bit early. Our chair will be, yeah, so our chair is Professor Santanu Dey from Mechanical Engineering of IIT Kanpur. He'll be here in 2 minutes, but we'll get him started just to give him some look ahead time. Okay, so his talk title is Primary Automation and DNS of Two-Phase Flows. And Dr. Anubhav Sinha is an assistant professor in the Department of Mechanical Engineering at IIT Varanasi. His research interests span hydrogen combustion and safety, two-phase flows, battery thermal management, flame stabilization, etc. He is currently leading multiple research projects in these domains funded by DRDO, DST, ANRF, MNRE, and other agencies. So with that, you can start.
Yeah.
Okay.
Thanks, Rajesh, for having me here and for this wonderful opportunity. And more thanks for having it quickly. So I will start with, this is my work which I wanted to present here, two-phase flow, where we have done some experiments as well as DNS. So I have planned this talk more focused on students. So I will be giving a lot of introductory information, and I am trying to basically highlight what are the challenges faced in this particular field of domain, so that if someone is willing to pursue a research career, so he can get some pointers. So that was the basic objective. Some of things may be very rudimentary for advanced researchers, but that was the plan. So I would start with telling the basics. What do we exactly mean by primary automation, and what is a DNS sort of I will explain, and then I will focus on what are the major issues or challenges that we face. Pointer, okay, that's fine. And then I would talk about some of the challenges which are there in this particular field and some of the challenges which I faced. And particularly I'll focus on something we did on inlet boundary conditions and some more related examples. So I wanted to show what are the basics of this field and what are the industrial examples where we can apply the knowledge of this field, which could be result in some useful work. Engineering examples, and I will basically summarize. So starting with primary automation. So the idea is that you have a bulk liquid which you want to break into droplets. So for primary, we don't talk about droplet breakup, but we talk about liquid jet which is breaking into ligaments and droplets. It could be, this is a liquid jet in cross flow, it could be a liquid jet, it could be a liquid sheet, it could be a straight jet. So all these are examples of primary automation, where we have a bulk liquid which breaks into smaller. So this is where we deal with, and the secondary automation is sort of well understood and characterized. And some basics of DNS. So basically this is the energy spectra, and if I want to do DNS, I have to solve Navier-Stokes for all the scales. You model approximate for RANs, but you solve because of that, you have to go to very small length scales and time scales. That is one issue that I will try to highlight. So these are the challenges I will deal. So I will separately deal with each of them. So I will just skip the slides. So basically, I'm trying to highlight what are the peculiar issues that we face for, especially for two-phase modeling. So one issue which is there in most of the DNS is that we have a wide range of scales. So if you look at flow field, so this injector could be of millimeter, but if I want to do some engineering simulations, I have to take account for some centimeter or of domain. So there's a large range of length scales. If I want to get the ligaments captured, so that will be of the order of 10 to 100 microns, or if I want to talk about sheet thinning, so that will further go in the micron level. And especially if I want to talk about droplet breakup, it will be of the order of 10 micron or so. So there's a large range of length as well as time scales which we need to resolve, which make this complicated. We also have to, like for breakup and pinching off, we need to have the very thin boundaries. And if I talk about two-phase where I have liquid and gas, so the interface is ideally should be zero thickness, which is very difficult to obtain in a computer simulation, but that is what is physically required. So basically it results in very high computational costs. So that is the challenge, and yeah, these are the droplets. So you can imagine this is in micron level, and if I want to capture the pinching of this type of behavior, so this is what I need to resolve. That makes it computationally very expensive. So once we start getting smaller droplets, so first is that especially for a two-phase flow, I need to capture the interface. So there are two fluids we have to model for the liquid as well as the gas phase. So these are the techniques which generally are employed, but each technique has some issues with it. Nothing is, I would say, perfect or ideal. So what are the issues involved, and whether for a particular case that is suitable or not, that we need to assess. Other than that is that in primary automation, we need to look into, this is like we make a hole or sheet thinning. So sheet perforation, ligament pinch off, droplet breakup and all. The challenge is that if I have an event like this, this will give rise to some singularity, and which will give pressure spikes and all that. So it becomes a challenge, and it also becomes very much dependent on the grid resolution. So if your resolution is not proper, then you will have different results that could be not non-physical. So these are the complex structures that we encounter, and we will try to get in these simulations. So this is a liquid jet in a high pressure chamber, which is modeled for a diesel engine. Okay, another challenge is that for proper breakup calculations, you need to have surface tension calculated properly. For surface tension, you need the curvature to be very accurate. Even a small issue with the curvature will give large errors for surface tension, which will result in errors in automation. So this could also result in spurious current, which basically gives you non-physical result. So it becomes very challenging to figure out whether what you are getting is correct, or it is some spurious result because of the artifact of low accuracy. So that is actually a very fruitful area of research nowadays. And we also have a large range of variation in properties. So when we would ideally like to have a step function jump from liquid to gas, but if you look at the properties, density ratio for water to air is roughly around 1000, then viscosity is 100 times. So these are the issues which basically make your momentum equation stiff. Then there are issues with pressure velocity coupling and all that. So these are the challenges that we face, particularly in a two-phase simulation. So consequently, lot of schemes which are working very well for single-phase DNS, they are having lot of issue, and most of them fail when you use the scheme for a two-phase flow. Another thing is that we have two-way coupling. So it is not only that the air is breaking up liquid droplets, the liquid interface also affects the air, and it may impact the turbulence levels. So you have to account for both of them. So that itself is quite computationally expensive. And another major challenge, because I am actually mostly from the experimental side. So experiments, you cannot get all the things that you would ideally want to calibrate or compare with your CFD or DNS. So for example, this is a spray. So sprays are typically very dense. So you don't have optical access. You cannot measure droplets near to the nozzle. So for example, in CFD, I get an Excel file with all the droplets, location, diameter, distortion, all that. But in experiment, it is simply impossible. You can get some point measurement at some point location, but you cannot get very reliable data, especially in dense sprays and all the locations. So that is one challenge. How do you compare that with CFD? So some quantities are especially, like for example, local curvature. It is very difficult to get in an experiment, which you can get in CFD, but in cases like this, in what is how your interface is moving. So this, especially particularly in dense spray. So some experimental techniques are coming up. For example, X-ray people are using, but how good your data is and how much you can compare with DMNS, that remains a burning question. Okay, now another issue that I would spend some time on is that actual injectors have some variation, and this is not very, I would say, DNS friendly. So you could have, because of the design and because of the imperfection in manufacturing, you could have the nozzle geometry is not perfectly smooth as we would like to have. So we could have some internal turbulence or cavitation, or even in engine you could have thermal gradients, which we generally overlook in a lot of CFD simulations. So because of that, we have to give in the inlet synthetic turbulence or some idealized inlet conditions which may not be correct as per if you compare with the experiment. So how do we solve that, and what are the consequences of that if that is not correctly modeled? So I'll start with one example. So this is a very famous, this is the, I believe, the most cited work on liquid jet DNS. This is from Shinjo and Umena. So they have done a lot of analysis on wave formation and breakup and all that. But the interesting part is that they've used an inlet profile which is uniform. So they are not having any effect of the, if you pass liquid through a tube, it will have a parabolic or a power law profile. And surprisingly, almost all the DNS literature of liquid jets, they have used the same profile, which is physically not correct. It will violate the no slip condition at the wall. And I was actually quite surprised. So there was this extreme, and another extreme is that this is not DNS, this is LES. So there's a group in by Agarwal and Trujillo. What they have done is they have took the actual injector, they have done some 3D scans, and they are trying to model that into their simulation. So one extreme is this, another extreme is this. So we cannot do it for all the injectors. We cannot take into account all the manufacturing inconsistent variations. But what to do? So one route what we thought about is we can try. So this is the same case which we have run with inlet velocity uniform. So what we thought is we will try using a parabolic profile. So you see the difference. So one thing is that if I have the same mass flow rate, parabolic peak velocity will be double that of this. Then actually most of the breakup is happening from the jet tip. So the jet tip is very different depending on your velocity profile. So the breakup behavior, the wave generation, everything changes drastically if you just change this, because this is the very critical parameter in my understanding. And if you look at the literature, everyone is using this profile. So they are getting some number. As I told, it is very difficult to match everything with the experiment because all other numerical schemes are validated. So they say that this is a good result, but if you're not careful, so you might end up with something. And this is basically the mid plane of the jet. So what it shows is that you can see the boundary. So because you have given a uniform profile, so there is no boundary layer. So here we see a very clear boundary layer which is developing in the parabolic flow. Now why that is important, we will see in the next slide. So basically the jet will develop some surface instability. That will happen because of this. I will show. Okay. So in experiments, what we have observed is that as the jet comes out from this, from the nozzle tip, what happens is that you have a no slip condition inside. As soon as it comes out, it becomes a free surface. So there is something called velocity profile redistribution. So that gives rise to instability on the surface, and which later goes on to break up the jet. So that we were able to replicate in the DNS study. So one thing to notice that we have not given any perturbation. This is just a uniform, not uniform, parabolic velocity profile. Ideally, for a turbulent case, we would need to have some fluctuations which will account for the inherent turbulence of the fluid. And this is basically, it shows how it goes out and how this waves start developing, and which basically breaks the liquid jet. And this we have shown experimentally. These are at the exact same operating conditions, but the nozzle was different. So only we have changed the length of the nozzle, keeping the diameter constant, so it becomes different L by D. So L by D will basically change your boundary layer development, and the boundary layer will impact the jet turbulence level and breakup, which we have shown in for straight jet, as well as this is jet in cross flow. So you can see for the exact same, these are all other conditions are same. For the same Reynolds number for different nozzle geometry, or I would say different velocity profile or different boundary layer thickness, we are getting very different behavior, as you can see in these images. So that basically highlights that it is very, very important that you, whenever you're running a very computationally expensive code, you have to be very careful with the boundary condition. Even a small mistake could result in a large variation. So that we need to account for. We have actually, this is a interesting study. So if you look at these jets, so these are again at the same conditions, and we have measured the wavelength of these jets, surface waves. And if you look at the literature of surface waves on liquid jet in cross flow, all the previous literature agrees that this wavelength is dependent on Weber number. So there's a parameter n, every other paper will fit different n, and they will say that it matches with the theory. The problem is that it again depends on the boundary layer thickness, and this is what we have derived. So we have shown that the wavelength will depend, it will depend on the Weber number, but it will also depend on the nozzle geometry. So if we account for that, we are able to get a good match with our data, and I'm not showing here. We have compared with whatever was available in the literature, and we are getting a very good match. So it further proves that you have to be very precise when you're talking about the inlet boundary, because that controls a lot of dynamics, especially in breakup sort of studies. Because these waves will eventually lead to further deformation and breakup. So we have to somehow account for them. So I will now come to another application of multi-phase flows. So this was done at the time of COVID. So this is the geometry of elevator. So I've used mechanical department. I've taken the dimensions of our department lift, and we have taken some velocity measurement from the fan. So usually if you look at the guidelines, we have social distancing guidelines that were based on MIT data, and that was done for a quiescent room. So I'm sitting in a room, closed room, I am coughing or sneezing, and they measure the distance, how long it penetrates. But the interesting point is that most of the time we have some ambient airflow which will affect the spray. So for example, we will have a fan or exhaust or AC duct which will have an airflow which will impact. So the question is how much? So if I look at this flow field, and mind you, this what I will show now is based on the actual measurement, velocity measurement from that fan. So that I have used as an input in the CFD simulations. So you can see that if you have a fan on top or near top of your head, this is from a cuff spray particles if you are coughing. So they get strongly deflected. So, and this model I am taking into account breakup, coalescence and evaporation. We have also shown that if you have different relative humidity, how it evaporates and so on and so forth. But this very clearly shows that this fan will have some impact on how far the spray can go. And we can also, I have done multiple cases, I'm just giving a brief overview. So we have also shown that if I, instead of fan, if let's say I have an exhaust fan, which will suck the air near your mouth, so that will also help to reduce the impact of this spread. So these are the type of things you can, this is not DNS, this is URANS only, but we were able to, we did some Lagrangian particle tracking. So some spray penetration, this type of studies we have also done. I will come to the another part. So we are looking into metal powder formation. This is a DRDO funded project, so we're looking into titanium and such alloys. So we want very uniformly sized particles with a smaller diameter, which is quite in a very controlled way. So what we are doing is we have a nozzle where this is a CD part. So we have supersonic gas which is hitting on a molten metal. So in a CFD, I thought that it has all sort of complicated things in a very small region. So I have a supersonic jet, I have a liquid which will basically disintegrate and form droplets, and it is not, it is comparatively much easy what we generally do. We do it for fuel sprays which are liquid, which can be modeled by water. But this is at a very high temperature, this is at room temperature, so how they hit, how they tear off ligaments, so it becomes very interesting. We are also planning some experiments, so we started with geometry optimization using CFD. So what we found is that we are able to get some data on droplet formation. So we have seen few different nozzle designs. I would say there's a very minor change in the nozzle geometry. But in spite of that, we are seeing that we get very different droplet size distributions because of that. And not only that, so in generally, if you have a fuel spray, I would be content with this sort of data. But the challenge is that we are dealing with molten metal, so it also gets solidified. So that part also I need to take care. So we are also getting data on droplet morphology. So we are basically looking at the degree of deformation of droplet. So if it is highly deformed, we are seeing fiber. If it is almost like a sphere, that it is called spheroid. So some number is there, I don't remember right now. So what we see for 3 different designs, we are able to change the distribution. So the first one is giving very less percentage of spheroids, while the third iteration what we did, we were able to get very small droplet size, and we are able to get most of the droplets in the spherical regime. So that is what we are trying to get. So these are sort of examples which basically we are trying to use CFD to give a meaningful result, and we are also, basically I'm more of from the experimental side, so I'm using CFD to optimize the experiment. So we'll do experiments and then we'll compare with this. So that is the objective. So I will just summarize. So I talked about primary atomization and DNS of two-phase flow. What are the issues? Some issues with two-phase flow and what is the importance of boundary condition. And some examples I was hoping to motivate some of the younger students to take up this sort of issues. And with that, I will thank the Param Shivai supercomputer in BHU, my students and collaborators and funding agencies. And with that, I would thank you for listening to me patiently, and any questions I would be happy to answer.
Thanks, Anubhav, for nice presentation and taking us through many simulation results. So the floor is open for any questions.
Yeah. Yes.
Yeah, thank you for the very interesting talk. From your DNS data, have you done some sort of like POD or DMD sort of analysis on the mode shapes that are responsible for that primary atomization?
No, actually we have done POD from experiments, but for DNS you need a lot of time steps to do that. So the computer will not, it took like 1 month to get that. So I have to run for a year to do POD sort of thing.
Okay. Yeah, thank you.
Like you mentioned, like the most of the schemes which we conventionally use for DNS fail with two-phase.
Yes.
So how do you like do it? Do you have in-house code, some solver?
Yeah, again I said I'm more of from experimental side. We have used an open source. What results have shown initially, DNS is from something Basilisk. That is open source code.
Okay.
So we have not even modified the code. We have used the code. We have given our geometry and properties.
Thank you.
Thanks. Nice talk.
Yeah,
so
thanks.
I just had one quick question. I think
Yeah,
I
sure.
missed a little in the in between. So you mentioned RANs
Yes.
simulations, right? So do you use that still to study drop atomization?
Yeah. So this all is using runs.
Right. So in such situations, the atomization won't it be, would it be accurate because we are not capturing the small scales and all
Correct.
the,
But
right.
see, RANs is basically used to get the ligaments and droplets. So the final droplet count, what you get, that depends on secondary atomization.
Right.
So secondary is, I believe, quite well studied. So we have different models for secondary atomization. Secondary is basically how you tune the model parameters.
Right.
So that we are again we have to yet to compare with experiments, but we are getting sort of believe I would say acceptable sort of data.
So for primary atomization, you're saying that the ligaments and so on, they don't depend so much on the small scale structures. Is that?
They depend, but we don't have. So we have tried DNS also. I have not shown the result, but the DNS, what we are able to do is a very okay. I will tell you something interesting which I did not wanted to get into. So we have done DNS for the same geometry, okay, but it is a very like miniaturized, very small compared to the actual nozzle. Now from here we are seeing that we are getting lot of ligaments and all. DNS we don't get that because it is so small it suddenly becomes spherical. So we can try DNS, but if I get Fugaku, I can do that in DNS, not in MBH. So
yeah, of course.
That
Okay,
is the
thank you.
challenge.
Yeah, thank you.
Welcome.
Yeah, it's very basic question.
Yes.
That you did DNS using that volume of fluid method?
Correct. Yes.
Okay. Or straight volume of fluid method,
Yes.
nothing else. Okay. And when you are visualizing these images, what contour have you used? I mean.
So this is okay. DNS contours you're asking about?
Yeah.
So basically, it is the liquid surface. So the basically the volume of fluid, the color function they use. So one is for the liquid surface. So on the liquid surface, I have this is showing you the velocity, axial velocity in x direction, superimposed on the liquid surface.
So when you simulated, you also simulated the air around it, right?
Yes. So basically, it is like a closed. So there is no airflow. There is a closed chamber in which we are putting liquid.
Okay. So you started with this two profile. One is uniform as well as another is parabolic, right? So if somebody gives this instead of parabolic the turbulent inflow, then the simulation will change, right? I mean,
yeah, that is what we are trying to do. So I have not shown. We have done one power law profile also. So that is also very different. But the challenge is that see, I am not quoting.
No, that's what you showed on scaling, right? So
yes.
That scaling is going to change then. I mean.
Yes, definitely. We have different levels of atomization. I don't have the slide. We can see different percentage of breakup with different profile. So that is very clear. Okay. Only thing is that I have not given any initial turbulence. So it is without inlet is without turbulence. After that it generates. So if that is the future work which we are planning to do.
That is very interesting. Yes, that's what.
Yes.
Yeah, very nice work.
Thanks. Yes. Correct. Yes. Double. Yes. I have not tried that. So I understood you're saying you keep it half. So but it will not be strictly speaking comparable. Correct. Yeah, but mass. Yes. See that there are two things. One thing is it is going longer, and then the basically okay. Let me go to that. So basically, most of the ligaments and droplet is coming from this jet tip. Actually, I will show you the zoomed in. Yeah, both are same time steps. So yeah. So a large portion of those droplets are coming from a region like this and this, which is the jet tip. So the tip shape is very different for a flat, and it basically that determines by the velocity. So that makes a lot of difference in the breakup behavior. So they're not comparable. Even if you do that, that behavior will be different. Sure.
So two things. One, these animations look, the colors look really nice.
Oh, thanks.
Second thing is, have people done linear stability analysis or something like that?
Yeah, there are a lot of people.
And if that was done, then how come people didn't use a parabolic profile before?
I am also surprised. Actually, I told my student, he did the same thing. Then I said, what? Then we realized that literature is filled with that.
Okay, but then, so the literature, does it show if you have a uniform inflow, you get breakup here, if you get a parabolic
So they are using uniform inflow and they are talking about their breakup. They didn't talk, no paper I couldn't find that talks about the parabolic and how it affects.
But even stability studies don't use a parabolic.
Stability studies they have given, but not in DNS. DNS, only thing I could find close was this paper. So there are one or two papers. What they have done is they have modeled the all. So this is one paper where they have done open form LES. There's another paper they have modeled this and they have run a DNS on the pipe and they are storing that data and using it for generation of that. So that is, I think, the only paper I could find which talk about this effect. Other than that, it is all flat profile.
Okay, thanks.
Okay. Oh, nice. Yes. Alias might, I am talking about DNS.
So I've not seen the literature, but I think, Okay, but let's thank the speaker.
Okay.
I think
thank
it
you.
was an excellent talk. Thank you. So our next speaker is Professor Preeti Malagar. Okay, 5 minutes. Okay, so let us take some break.
Please be seated. We'll resume our next talk within 5 minutes.
So our next talk is basically high performance end-to-end weather simulation, prediction and visualization. It will be delivered by Professor Preeti Malagar. She is an assistant professor in the Department of Computer Science Engineering. And she basically works in high performance computing, scalable parallel communication, workflow optimization and related areas of scientific computing. So she completed her PhD from Indian Institute of Science, Bangalore. And before joining IIT Kanpur, she worked as a postdoctoral researcher and assistant computer scientist at Argonne National Lab, as well as she has a visiting affiliate at Lawrence Berkeley National Laboratory. Thank you.
Extremely sorry for the delay, and thanks for the kind introduction. So I'll be probably talking, my topic is probably an outlier here. I don't work in physics, and I'm not a computational scientist, but I'm a computer scientist by training. But I do a lot of work using the simulations that many of you write and work on. So first of all, thanks to Rajesh and Pradeep for inviting me. This is a different kind of crowd. I'm not used to speak to people not from my domain, but hopefully I can give you some insights on what we have been doing. So you are all familiar with this pipeline, right? We write a lot of data. Your simulations write a lot of data. And then you analyzed also. I don't know if Aditya is here. He told me that yesterday he writes 25 terabytes of data at the end of the simulation. So it's very hard to process even that terabytes of data, right? If you look at the news of the Higgs boson particle, you will see the analysis took 6 months of time. That was the article that they had mentioned. So basically, one of the bottleneck is the disk, right? We are very much used to write to the disk because disk has been there for a long time, and there's a good reason. It's cheap. It's a lot of storage space is available. So the problem is that because you write a massive amount of data, it has been probably more than 10 years that architects have come up with a different layer. So there's a hierarchy of storage now. You don't need to directly go to the disk if you can, right? So I'll talk about some of those aspects. Okay, so just skip through the bullet points and come to this graph. So this graph shows, although it's a little outdated, only in 2018, so it compares the compute rate and the I/O performance. So you're computing at a very high rate, right? You're capable of computing at a very high rate, but you're not capable of writing or reading at that high rate. And so hence, this is true even till date. So the ratio is kind of decreasing. What that means is you're computing at even more and more higher speeds, but your speed of reading and writing is still almost similar or marginally different, right? So this is one experiment that we did, Deepak did as part of his thesis. We were looking into using something which is not a disk, right? It could be a non-volatile memory, it could be even DRAM, right? So this is the performance difference. This is your disk, and this is your DRAM actually, DRAM on Param, right? Our Param Sanganak, and you can see the difference. So these are different process combinations, and these are like simulation analysis process ratios, and you can see there's an order of magnitude difference. So what can we basically do about it? And same picture, basically, DRAM on Param and luster on Param, so the bandwidth, so the blue versus blue and the orange versus orange, so read and write. So both you can get, order of magnitude difference, a lot of difference, right, in the performance. So if you carefully look at your simulation I/O performance, you will see the simulation time step is probably in a few seconds, and then the peak of I/O time will be like 10 seconds, 5 seconds, depends on how much you're writing and so on, right? So this is a kind of slightly older graph, but it kind of tells you the picture. So there is DRAM and there is SDD that we know about. There's also SSD, and there's something called non-volatile storage. So basically the latency kind of increases in this order, as well as the price decreases. The bandwidth sort of is similar or even lower as you go from top to bottom, right? So, and these are various numbers from different papers. So there's a lot of work in this area. This is the Frontier compute node. Frontier, I'm sure all of you have heard of, and you can see there is a 512 GB of DRAM, and then there is NVM SSD of some terabytes, 2 into 2 terabytes. This is on node, per node. But if you rely on your older API, they are probably, if the APIs have not changed, right, then you will be automatically writing to the disk, basically, right? So I'll talk about some of our work, what we did to kind of use this kind of, on-node storage. And this is another picture, again, from some recent paper where they compare the SSD and the RAM disk. RAM disk is what they refer to as NVM, and you can see the throughput is order of magnitudes different, right? So this is Fugaku's architecture on node, and even so you will see it has an on node 432 GB high bandwidth memory, right? So, and there's a reason for this. Why? We already discussed the I/O bandwidth is very slow, the disk bandwidth is very slow, right? This is from Intel's, again, so I mean, various vendors are, and this is a very recent article, December 19, which says still can't meet demand, right? Okay, so what we had done is, this is a slightly older technology, so to speak, 2016 or 2017. And as much as funding I could only get 2 of these in the local systems that I have. So all my experiments, many of my NVM experiments are based on this. This is from Intel. Okay, so again, some more motivational number. One thing I want to tell, so when you read papers, you have to read very carefully, right? Here you will see, I already told you that there is some performance similarity as well as difference. So it depends on the technology. So DRAM, NVM, both are based on different technologies and they evolve, right? So you'll see there is some difference. There is an Optane node which has both DRAM and NVM, and there's a DRAM node which doesn't have the NVM. And you will see there is some numbers quoted here. Here, you will see that the numbers are significantly lower. You will see that why would I use this, right? But the problem is, in this paper, they have actually configured this as a block device, and that automatically gives you lower bandwidth. It should be actually configured as a memory. Okay, so this is what the students, when you read the paper, don't just look at the table and assume. You have to read the, the fine print. Okay, so now, so what did we do with NVM, So the case study that I'm going to talk about is tropical cyclones prediction. And what we'll do is, so our simulation is basically a weather simulation and doing a deep learning based cyclogenesis prediction on the fly for the weather simulation using a non-volatile disk. So first I'll talk just about the framework, because we spent, or one of my MTech students spent a lot of effort in actually coming up with this framework. So hurricanes are not new. You are well aware of hurricanes, typhoons, and cyclones, right? And this is 2005. This was very much in news. It caused a lot of fatalities, and so much so that even after 12 years, they have articles saying that after 12 years, the devastation is still humongous, right? What changed in 20 years? This is last year's. Still there are fatalities, and the reason is it's very hard to predict typhoon or cyclone or hurricane with sufficient lead time. If you don't have sufficient lead time, then you can't do much about it, right? That's the problem. So anyways, this is again from Wikipedia, some category 4 or 5 cyclones in India. As you can see this path. So these tracking this, so there are various challenges. So, where this is going to make a landfall, it's very hard to predict where and when. And so IMD gives some, some prediction with some lead times, maybe 1 or 2 days. I'm not sure what is the current situation, but it's not a very significant amount of time, right? So we took up this problem where, so there is a very good signature of cyclone is it has a very low pressure area, but this is only after when the cyclone is formed. During the genesis stage, it's very difficult to predict because there are several of these depressions all over this region, okay? Which of these will actually mature, and only one of them matures. Which of these will actually mature is very hard to predict. And hence, the goal here was that we will look into this problem so that we are able to get at least significant lead times with some reasonable accuracy that has already been there in literature and so on. And the lead time also comes from the fact that how fast you can analyze the data, right? Okay, so with that, one of the important challenges, like I said, it's very hard to predict. Hard to predict because it's not a very well-defined process yet. And what we did initially is, so we did a lot of literature survey and so on and so forth. And what we did is, so running a DL is also a costly phenomena. You have a terabyte or, well, 1 times maybe some GBs of data, and you don't know where to, kind of analyze. Every point has to be analyzed in the knife scenario, right? So what we did is we first wanted to filter out some data so that we don't give entire data to the DL, right? So we did a 2-step approach, and this is the overall framework. So this is 3 years old work by one of my MTech students. And so this is the first thing that we did is we inserted a trigger, which is these are possible probably some regions which could mature into the cyclones, and then we fed only those points which was yes to the prediction model. So this trigger-based mechanism, basically we looked at some of the, specifically these 3 variables. It was very simple. We didn't want it to be too costly because simulation is already compute intensive. We don't want a more compute intensive process in the way. So we did a very simple thresholding based mechanism, and it was, in fact, it worked very good in terms of accuracy, but the problem was there was a lot of high false alarm rate. So we had to reduce that, right? And so this is also possible with a good lead time, right? So in order to do that, we had to, one thing you have to know is out of the 100 meteorological variables that the simulation is is giving as output, you have to know which ones to look at, right? So we did a lot of literature survey, and out of that we selected these variables. So on the fly we had to analyze these variables, and this is a network that Abir, the student, he came up with after a lot of iterations. Initially we were looking at LSTM, it didn't work that well, and so this is kind of, the details of the network. But well, what I want to focus on is in the compute and the data aspect and end-to-end time, right? So we looked at this. The simulation that we were running is this WRF. It's called WRF, Weather Research and Forecast Model, and it it's a numerical weather prediction system, and this kind of, so this shows the process decomposition. It does a 2D process decomposition. And the data set that he actually worked with was around like 60,000 data points from this 165 cyclones. And we had to look not at the IMD data that was available, but the data that was generated by simulation, because that is the data we will be inferring on also, right? So so this model performed pretty well, and so we were able to also reduce the false alarm rate up with a good lead time. Now his whole thesis period went in developing this model, so I had to employ another student to now optimize further. So we started, he also developed a kind of a prediction GUI to just show, right? So what we started analyzing what were the kind of the performance bottlenecks in this whole pipeline. And so one of the problem was there were multiple triggers all over, right? And so it is a simple thresholding based mechanism. So unnecessarily there were like a lot of triggers. So these are the single points. So there were a lot of triggers just in one process, and nothing much will change if you just use the centroid, right? So what we did is, instead of feeding all of this to the DL model, we just created these centroids of the clusters we clustered, and just use the centroid for the further prediction. And this is the kind of reduction you can get. So from 462 MB to 11 MB and so on. So every MB counts actually, because you are resource, in some sense you are resource bottlenecked, your network bottlenecked, and so on, right? Okay. So going forward, so this was the work that was done by Deepak. So he basically, what we did is, we had this hybrid kind of mode where we used NVM and DRAM for different purposes, because although NVM has a lot of space, so we have the capability to store a lot of time steps, and we can do the analysis. DRAM is space limited because DRAM is costlier, right? And so what another thing that we did is, we did an importance analysis before we even wrote, no matter to DRAM or to NVM, for further storage. So why we did this is because if you look at your output, the time step, the difference, so this is a visualization of the weather data for one of the cyclones, and you will see that these two are not too different, but these two, there's difference between the first two. And so it makes sense to, even if you've written this time step, you should probably also write this, and it's okay to skip this. So these kinds of on-the-fly analysis, again, these are all in memory. And so if you remember, I told that we replace this disk with this NVM. so to do the on-the-fly kind of analysis. So the bottleneck, the disk bottleneck is sort of gone. However, the simulation is faster, right? So we don't know which time step to write and so on. So you still cannot be writing every time step. So you have to be very cautious about what time step to write and so on, right? Okay, so now the question is, one question is, I'm telling you that I'll replace, I'll use this, a different, memory. But the problem is, if you see simulation codes, right? So here if you see, there is a API, right? This is part of WRF IO code, and this is just a small, very small snippet. And somewhere down it will call these kind of calls, which says that, write this variable. And this is something hidden in some 100,000 lines of code. You don't want to actually modify the code, right? But you still want to achieve what we achieved. And this is from another snippet from S3D combustion simulation code. And again, you will see calls like this, right? So these are netcdf APIs to write a netcdf file, right? So what we did was, so to analyze this time step, without changing the code, we had to actually, so we developed something called PQ, which is, just a parallel, it's a replacement for pnetcdf, which is what is used for, is an API to write netcdf files, parallel netcdf files. And what we did was, we just inserted our library. So we compiled WRF with our library. So our API can be seamlessly integrate with any simulation code that writes the netcdf file, kind of files basically, okay? So there are some challenges, and you can see we tried to keep the APIs very similar, right? You do not have to call this. So whenever the code calls any of this, it actually calls, in the backend it calls our APIs. So we don't have to change the simulation code, right? We just need to compile it with our library. So there are some nitty-gritty details about these. I will probably skip these. So the issue is that you are writing multiple time steps. There's a simulation writer, there is a reader, so you have to synchronize and so on and so forth, right? And there are multiple processes. So towards that, we had to spend some effort in designing this. Another point I'll point out is, so you can see there are 16 simulation processes. And what we are doing in analysis is not as compute intensive as the simulation process. And so you do not need 16 processes in some way. If you think of Param, we have 48 cores, so which means you are running 48 processes. If you see the scalability between 40 processes and 48 processes, it's very marginal. So you can as well use 40 simulation processes and 8 for analysis on the same node without even transferring the data to the disk, right? You're using that on-node memory, local memory storage, right? So so this is an example where you have, 16:4, the ratio. And these are some of the results. So basically, PQ write gives you the time required is very less, and the x-axis is data size, the y-axis is time, and the red is the pnetcd, which is the default, and the blue is the PQ write, which is our API using NVM. So without going to the disk, basically, right? So the one other thing that I want to point out is not only the IO matters, in fact, process placement also matters. If you have a 2-socket node and your simulation, so 2 sockets are connected by what you call network on chip. It could be a QPI or UPI-based interconnect. So the 2 sockets, so 48 cores is like 24 cores. And if you have all the simulation process on 24 and plus some on the other socket, and then you are doing all the data transfer on that same interconnect, that also matters. So we played around a little bit with the placement. You can compare the orange bars, so that's the analysis, and the simulation times the blue ones. It's higher because the analysis time is higher because the number of cores is smaller. But it does matter. So these are different placement. I can take this offline, what that exactly means. But what it means is it tries to take care of the network on chip to do a data transfer which is not causing too much congestion on the network, basically. Okay. So finally, this is like a depiction of the whole scenario. So the simulation progresses in its set of processes, and so this is a timeline, right? and this is, say, running on 512 cores, and this is on some 16 cores and so on. And we have the triggers, the clustering, the prediction, and so on. And still you have some time, right? Because, like we said, the simulation, first of all, the simulation time step is not costly, is more costlier. And secondly, we have probably done the analysis only every 60 or whatever, 1,000 time steps, right? Every hour or so. You can, of course, decrease that, but that's up to the probably the application and the developer, right? But what we did was we took this a step forward, and this is my PhD students' work. So where we not only looked at cyclones, so we looked at more extreme events relevant to the Indian scenario. So these are the 4 extreme events that we looked at, and this we already know the data size is huge, and hence here also we continue using the the RAM, DRAM, or so on and so forth. So here you can see again the simulation is probably running on some 8 processors, and the deep learning is running on some 4 processors. We also do visualization on the fly, so everything is on the fly via the memory, and there's no disk involved at all. So this network is slightly different from the network that we developed for the cyclogenesis, and this actually is kind of able to classify 4 kind of different extreme events. So we use something called ADIOS, which used the memory. It doesn't use NVM, I think. So it uses just the DRAM, right? So you don't, you can plug in ADIOS, and so simulation writes to DRAM, and from DRAM you can do the analysis. So for the training, we used distributed training, distributed TensorFlow specifically. And so this is the more important part, the inference. So when your simulation is running, you want to do the inference also on the fly, and you don't want to go to the disk and so on. So you can easily use that on-node local storage, store the data, analyze, and then predict yes or no, or what kind of, in this case, classify what kind of event it is probably, right? Further, we also did visualization on the fly. Again, data matters. So we didn't want to, be the data transfer be a bottleneck, and hence we pruned some of the processes data. So if your simulation process has, 5 and 2 processes, maybe not every subdomain has changed. In this case, maybe only some subset has changed, and we do that kind of analysis, and hence you can see that only 2 and 3 are transferred, the rest are kind of patched with the previous times, assuming that there was not significant change. So these are the sort of the events that we actually looked at, train, test, and so on and so forth. This includes all the 4 different kinds of events. So the student had to spend quite a lot of time in sort of labeling the data for training, and that's, I think, one of the biggest challenges in this kind of work. So this is the result of this online, prediction using WRF simulation and so on. And you will see that landslide and snowfall has slightly lower accuracy. So in July or August this year, there was this sort of a heavy rainfall in IIT Kanpur, and the day it rained, so here we have a school called Campus School. It was almost flooded till the gate, and we were kind of walking, our shoes under water and so on. So the next day, DM, the district magistrate, he declared a holiday. It's like a rainy day, yeah? That day, it did not rain. It was sunny. So, it's very difficult, challenging to predict the rainfall kind of events and so on. So, snowfall and so on. Okay. So, with that, yeah, so this is kind of because the inference takes a little longer here. You have sort of 4 different events being classified and so on. These are the strong scaling results. So you have, one thing you can see is simulation time kind of scales better than the inference. So this we have, even though here the inference is like, we do the inference, so we have no across node transfers. So the inference is the simulation process on node, the inference runs, and even then you will see that the inference time scaling is not as good as the simulation. And this is some of the other results using the transfer. So if you had transferred the entire data, your time would be slightly higher, obviously. And since we transferred only the sort of the important frames or subdomains, we have a slightly better performance. So all of these counts towards this, 41% savings. And so your 1 year of simulation time can probably go to 6 months or so, or 7, 8 months, right? So yeah, with that, I will conclude my talk. Right. So I want to acknowledge all of these students. It's mostly their work. And yeah, of course, Param also. Thank you.
So thank you, Professor. Thank you, Professor Malakar. So the floor is open for questions.
Hello, ma'am. So you are training the model for multiple processor. So
the training is also parallel, yes.
So like what kind of parallelism you are using?
No, so we don't actually parallelize the TensorFlow at all. So TensorFlow itself has distributed, there's a distributed TensorFlow version also. And in fact, PyTorch also has distributed PyTorch. So we just use, their APIs.
So basically data parallelism.
Data parallelism, yes. Mostly data parallelism, yes.
Actually, I don't have a question, I have a problem. So in Param Sanganak, in high memory nodes, actually most of the processes, they are not utilizing the DRAM, like 750 GBs of DRAM. So can you make something so that the processors which are running in high memory node, they get shifted to the 150 GB RAM memory nodes?
No. So the high, the question is asked because of a different reason. But high memory node means your DRAM is larger. That's it. There's no separate DRAM.
But some processors, they don't utilize.
So that is the problem of the application, no?
Yeah. But that's what my problem.
So we have to analyze the application, right? If you're, if it doesn't use, it's okay. So we have to take this offline because I need some more information.
Ma'am, regarding when you read or write, that is dependent upon like if you see extreme event or if there is a change from the previous time step information.
Yes.
So that is dependent upon the local.
No. So that subset, the change. So there are two levels. One level is even if you want to analyze this time step. So you want to store it because the analysis process is like, the consumer process. Whether you want to stall the producer process at that point or to put it a different way. So you want to store it, and when the analysis process will, consume the data, whether you want to store it or not, that is based on a kind of the importance. So it's a simple metric-based approach. So whether there was some change in the time step and so on, right? But there's another level where we want to transfer the data for visualization, right? There we consider the entire, subdomain, and we do sort of a diff kind of analysis and so on.
So then, like the global domain, or not.
So see, the analysis is actually done at per process level. If you have 512 processes, we actually compare this current time step with the previous time step that we have. Of that process, yes. Because, okay, so there is one assumption here that the subdomain owned by the process doesn't change. So this is slightly tricky for adaptive mesh kind of refinement kind of simulations, yes. For that, you will have to do something else.
Thank you.
Thanks, very nice talk. So you talked about an API. Does the hardware also have to be configured in a slightly different way for this to work?
Right. So the NVM, like I said, the NVM can be configured in. So Intel had one machine called Intel Night Landing, and they could configure it in 3 different ways: cache, extended DRAM, so on and so forth. Yes, that is possible. But for our experiment, we just configured it as one mode, like memory, and we just used it for our experiments.
But so, I mean, the NSM hardware, is that configured in that manner?
No, our Param Sanganak? Unfortunately, No, and well, I've tried to enable that. There were some challenges not from our point. I don't want to, maybe we can discuss offline, but yes, it has to be configured. There is some challenges because there are multiple users writing to that node. Once your job is gone, there has to be some cleanup or some initialization to be done. Yeah.
And the other thought I had was, so this writing happens to the NVM.
Okay. I mean, it can happen to DRAM or NVM. If you don't have NVM, you can also use the DRAM.
So is the NVM permanent, or is it?
Yes. So it is part of the hardware. Yes. So yes, you can assume it's permanent.
Will it eventually be written to disk?
Oh no. So it is persistent memory. Okay. It's your onus to write to the disk. Right? Okay. It's not going to be automatically written unless you have another API which is doing that in the backend, which Cray actually had, which is called Data Warp, and they used to do this. So, but well, it's another API, another level of API that we have not done.
Okay. So because I mean, the idea is very nice that you write to non-volatile memory. But it just feels wrong that you throw it away, and I mean,
we throw such a long run, right. So we throw away the time steps only after analysis has been done, assuming that we don't need it. If you do need it, then you definitely have to write it. And if you have that logic that yes, I may also need this in future, then yes. So the thing is, instead of writing 100 time steps, you can asynchronously write. Parallelly, another thread can run and write. So you don't bottleneck the simulation process as such, right?
I don't get one thing. We have been generating some data some 5-6 years back, and we are still using it. So we need that kind of data.
So the thing is, so I'm not advocating here that throw away all your data. What I'm advocating is, if you need, so things like extreme event sort of analysis, right? You don't want to write to the disk and then read from the disk, because there is a lot of delay, orders of magnitude difference. So if it's kind of an urgent real-time decision-making situation, you probably better use the DRAM and NVM if you have. And like I said, every node has HBM these days.
But that's an obvious thing to do. So I don't understand.
Obvious thing to, which one is the obvious thing to do?
Say if you don't want the data, but you want the analysis to be done and get the data out of
right.
that.
The thing is, you need to, so what I showed is that without changing the simulation code, where the simulation code actually calls MPI IO. Underlying is, MPI file write all. The higher level API is NC, MPI, put, bar. If you look at the simulation IO code, right? That by default will write it to the disk, right? So we had to build this API so that it doesn't by default write to the disk. Without changing the simulation code, it writes to the memory.
Hi, Preeti. Nice talk. Nice talk. I just said, I think I missed this part. So if I understood correctly, you said that, for example, 48 cores, you said 8 cores you would...
I just said as an example, let's say you analyze your scalability. If you see the scalability, I don't have a graph where I show the scalability saturation, right? It saturates at some point. Now, if you do 40 cores per 16 nodes versus 48 cores per 16 nodes, the difference, let's say your difference is a few seconds or some minutes, right? And so that remaining X number of cores, you can actually use it for analysis, visualization, whatever else you want to do.
Right.
So that was the point.
But in that case, like, for example, so what I mean is like, when we do CFD analysis and so on, do you see this kind of a behavior?
Yes, in the sense that any simulation, if you do the analysis and your per process, you can do the analysis with the per process data, even if you need to communicate. So I have not shown here, but earlier I have done MD simulation analysis on the fly where you need to communicate. You do all-to-all simulation, communication, but it's only among the analysis processes, right? So even if you need to communicate, you can use just those 8 processes. That's a sub-communicator. You communicate among those.
You can make a group out of those alone.
Yes.
But I'm still curious on like how, you know, that...
that split?
No, in the sense that you know, like 8%, I felt like load balancing wise.
No, so that's the point where we work on performance modeling. So we say we kind of predict on 5 and 2 process how much time it will take, right? So that's another research area. But for, I mean, if you have run your simulation enough number of times, because you work on one simulation, right? You have an idea that what is the scalability characteristics, right? So you can use that historical data also.
Maybe we have to go back and check and see whether this is useful for us and what's the balance.
Yes,
what's the right number and so on. Right?
Yes.
Right. Okay. Thanks.
Okay. Any more question? No. If not, then let us thank the speaker.
we'll have a short tea break for short time for 15 minutes. Then please rejoin us for a panel discussion.